Um, I hope you are able to see the screen, classical computers.
Yes, sir.
Okay, great. So, before we get into understanding what is a quantum computer, let, let me take a step back and give an overview of how our classical computer that we all are used to working uh, basically works. The basic premise of a classical computers were bits. Bits at any point in time can hold a specific value, and effectively these bits were handled by gates which are part of your processing ecosystem that is already inbuilt on the classical computers. Typically, when you are writing your high level programming, and these programmings will get converted into the lower level bit using various intermediate steps in terms of compilers, assemblers, and so on and so forth, and they will take care of converting these details into a bit level so that the computers can actually understand and process the details that is required. And we all are aware that a bit in a computer, in a classical computer, can hold uh, at any point in time only one certain value. If you take a bit, it can either can have a 0 or 1 at any point in state. Okay, this is a classical computer. Now let me take an analogy of a simple coin flip. Okay, assuming that you are having a coin and you are flipping the coin. When you are having the coin on your hand, you could be seeing the value of the coin in front of you. It could be displaying to you a head or tail. And assuming that you are tossing this coin, as I am showing it in the screen, when you are tossing the coin, when it is in the transit, in the motion, what would be the value of that coin? Any guess? What would be the value of the coin? If you can write it on the chat, what do you think would be the value of the coin when it is flipped? Exactly. So um, it is not indeterminate. That is true. But you can also mention the fact that you could be having both head and tails, right? You could be having both head and tails, and it is not indeterminate. That is true as well. Now, this is the basic premise with which the quantum computers basically work, where certain subatomic particles in the world at a certain temperature level, what happens is these atoms exhibit the quality of being available at the same time, both heads and tails. So that is a basic premise of a quantum computers. Okay, let me explain to you in detail. Uh, Coin at the stable stage were compared to a bits in the classical computers. You have a stable coin, and you can see what is the state of that particular coin. At any point in time, it can have either 0 or 1. That is the basic premise of a classical computers. Now, coins on the tossed state are considered to be as a special characteristics of a quantum computer called a superposition. So in the tossed state, as we have known that a specific value, it can hold both heads and tails. It can hold both heads and tails. And because it is a special kind of a property at a special stage, these qualities are termed as quantum bit. So that the quantum bit, the qubit, are the basic premise of a quantum computers. Hope I'm making sense, right? The coin at the stable state, you can compare it in terms of a classical computer bits. A coin which is uh, in the actual solved state could be compared a, in terms of a quantum computing superposition state, where it can have both heads and tails uh, at the same time, and these are called qubits. These are called qubits as such. So that is exactly what we are actually representing here. At any point in time, the classical computer can have either on or off state, but in the case of quantum computer, it can have both 0 and 1 at the same time, and this position is called a superposition state from a quantum computers as such. So how does this is achieved? Basically, now we all are aware, we have our laptops, we have our desktops, and all these laptops and desktop work in a typical room temperature currently we are used to. But to achieve this superposition level, the quantum computers should be kept at a sub zero temperature level. Not just sub zero, it is a very limited amount of temperature that should be there to enable the qubits to basically uh, come up, and the actual superposition can be absorbed only at that particular environment, not in a typical environment like currently we are used to in terms of room temperatures and so on and so forth. So this here is an example of how four different bits or four different qubits, which are actually continuously changing the value when they are in the superposition state. When they are in the superposition state, this is the basic premise of a qubit. That is the basic premise of your quantum computers as such. Okay, so the whole presentation that I was looking at, there are multiple ways from the quantum computing point of view you can look at, and quantum machine learning point of view you can look at for enabling this. I was looking at from a programmatic point of view. There is a mathematical point of view as well. You can have a complete session focused on math. That is also possible. But currently, I restrict that math part of it just to give a simplified information and also try to take you from a programmatic point of view, so that how we can actually utilize the concepts of quantum computer part of our machine learning operation. So that is the goal of today's presentation as such. Okay, so now this is as an example quantum computers, not like what we are used to. These quantum computers are pretty complex and has to be maintained at a very sub-zero temperature levels, and only at a certain temperature level that these superposition states of qubits are absorbed in the quantum computers as such. So how do we actually, if you're talking about such a sub-zero level, temperatures, how do we basically, utilize these quantum computers for our operations as such? That's a big question from a programmer point of view, and we will solve that shortly on that. But effectively, this is a sample quantum computers as such. Now, if you look at who are all the different players in the quantum space, these are some of the players who are part of the quantum space, and some of the big guys in terms of quantum is you have IBM, D-Wave, Google, and Microsoft were doing pretty good in this space. Even AWS have recently started their own quantum solution as part of their cloud delivery as such. So here, from a quantum computer's point of view, these are the providers who are actually making strides. And here on today's session, and we'll be purely focusing on Google-based quantum computers, and how we can actually utilize Google's quantum computing, frameworks for our actual implementation as such. But if you look at from a programming point of view, I will come to that in a minute. But there are many different frameworks and libraries are available which can actually help you start programming on the quantum computers as such. Right. So these are different players, and Google as such in 2017 released their bristlecone quantum computer chip. The bristlecone quantum chip was mainly used for research activities and creating algorithm and so on and so forth. It consists of 72 qubits. Think of we providing only 72 bits in a computer for your processing. Would you accept that? Now we have the processing powers in many millions, but we are at the stage of very initial stage of quantum computers. That's the reason that we have a very limited number of qubits are being used for building these quantum chips, because the technology is at the very primitive level. That means we are almost around 90s or 2000s when the computers were starting, when your Celeron processors, or even before the Celeron processors from the Intel. That is the level, that is the stage we are currently in from a quantum computer's perspective. So in 2018, they have built a Sycamore chip. Google has built the Sycamore chip, and to compare the capability of the Sycamore chip, they were able to achieve 2 to the power of 52 times of processing. And they have also mentioned that they have achieved the quantum supremacy. What is this quantum supremacy as such? Meaning, if you can perform a specific set of activity on your chip, on your quantum chip, if that activity cannot be performed on a classical computer, or let's say a supercomputers that you have in your presence, that represents you have achieved the supremacy. So now they have achieved it just with 40 qubits. Think of, to give you a comparison, whatever the operations that they could achieve in 3 minutes 20 seconds using Sycamore chip, it would take a classical supercomputer a 10,000 year to actually achieve it. This slide will give you a potential of a quantum computer as such. Okay, so the actual supremacy, the quantum supremacy, they were able to achieve just with 40 qubit, and whatever that quantum computer can achieve in 40 qubit, currently we don't have a supercomputer that can actually perform that calculations. That is the level. Now think of if we go in thousands or in millions of qubits. So so that's where we are ahead. We are going ahead. Just last month, IBM released that they have a quantum computing chip with 1386 qubit, and they are working on building a 4000 qubit processor by they wanted to release by 2025. So think of the kind of potential that the quantum computers can provide. If 40 qubit can actually surpass the supercomputers, the amount of things that you can achieve on 4000 qubit is unimaginable. So that apart, so how do we actually interact at this point in time? We are telling that you have a quantum computer which is which has to be kept at a subatomic level, and if it has to be at sub-zero temperature level, how can I hold that quantum computer for my operations and so on and so forth? So effectively, the current approach that you follow in terms of quantum computers, where you have a source code. In a typical classical computer, you have a source code, and you basically compile the source code, and the compiler convert that to a machine code, and that machine code gets executed, you get the output. So typically this is how the compilers basically work in a classical computers. Now let's look at from a quantum computer's point of view. The typical classical computer goes through the process in a very linear fashion, where the things are getting executed in a very linear way. Even though we are talking about some of the parallel processing within the classical computer, we cannot compare the kind of parallelism that is being brought in from the quantum computer. Now, the kind of parallelism at individual qubit level, that you can achieve a lot more within a very second of your quantum computers as such. If you have a 4 qubit quantum machine, and you can get the value of all the different combinations on the first single step itself. That is the because all the qubits will possess and exhibit the exhibit both zeros and ones at the same time. You can process all the values on the first step itself. But in the case of normal computer, you may have to go through a serial process, a linear process, to actually process probably 15, 16 steps that you need to get the details. So that's a major difference between these two. Now, how do we differentiate the classical computers? In what way that uh, it is different from a classical computers? As we said, uh, it has qubits which can actually represent zeros and ones at the same time. And as the power increases, the exponential in proportion to the number of qubits. Now in this case, the power increases only through a linear way in the case of classical computers. One other problem that in terms of a quantum computer is because of a sub-zero temperature level, and you have to maintain this superposition of this qubit. All these brought in a lot of errors in terms of calculations and so on and so forth. So as we speak, as of now, we have very high error rate in terms of quantum computers. But the advantage of classical computers where that it has a very low error rate, and currently if you look at, it is well suited for some of the optimization problem, data analysis and the simulation at this point in time. So when machine learning as such is basically an optimization problem, and that is the quantum computers were very well suited in terms of alignment with machine learning specific operation. And in the case of classical computers are best suited for your day-to-day activities as part of your actions. So that's a basic difference. Now let's look at what are all the different players from a programmer's point of view. What are all the different frameworks which are available and how they stand, what happens there. Okay. So the left side, it defines uh, the quantum universal languages, and is there any full stack libraries, and quantum algorithms, quantum circuits, assembly language, and hardware. So there are multiple different top players in the whole space, and some of them who are actually completing full stack that we will see here. If you look at, the full stack is available in terms of IBM and Rigetti, Zandu, Google, and Microsoft, where some of the big players who has the full stack details as part of your quantum computing as such. Out of this, if you ask me to rate them in an order of top players, right now, if you look at IBM and the Google, were leading this along with D-Wave as well. D-Wave main focus is on basically the hardware part. The hardware part is basically controlled by D-Wave, but the IBM and the Google were able to bring up their own set of um, programming stack, and that helps you actually start working with the quantum machine learning and the quantum computing resources. So now, if you look at from an IBM point of view, they have something called Qiskit, and the Qiskit as a open source library can help you start interacting with the quantum computers as such. Uh, they have packages in terms of Qiskit algorithms, and you can utilize part of your quantum computing resource. And the quantum circuits can be created and manipulated using Qiskit itself. We don't know what is this quantum circuit. We will cover that in detail with practical as well. I will come to that in a minute. Okay. And the second one is Google. Google has their own open source package framework called Cirq, and that Cirq acts as a full stack library for them, and anything and everything that you wish to do, you can do using Cirq. In today's session, all our practicals were focused on Cirq as the framework for your quantum machine learning implementation. And they also have all the quantum algorithms created using Cirq. There are many other items were also available. For example, in the case of healthcare specific, they have Open Fermion, which is a healthcare specific library to focus and the process the details. And the quantum circuits can be created using Circs as well. And the beautiful thing about uh, these two providers is IBM provides option for you to use IBM's quantum computer as a cloud-based access. So you want to create your programming for the quantum computer on your local machine, and you wanted to execute these quantum algorithms on the device, on the original device. IBM provides this as an option. So does Google. Google also provides their Sycamore devices, Briscone devices as a cloud accessed devices for executing your quantum algorithms directly on the devices as such. We're going to see how we're going to do that as well on today's session. So that's the beauty of these two providers. And also Microsoft has their part of their Azure stack. They have a quantum developer kit and Q sharp and so on and so forth as part of their quantum project. as such. So in case if you guys have any question, just put it on the chat or ping me so that I'll be able to answer this. So from the evolution perspective, if you look at in the 1950s, we had our assembly languages, and we had our discrete wires circuits where we have written the program on assembly language and executed them. And the evolution as such brought in our classical computers, and you had your high level languages compilers which can actually help you translate your high level language details to specific hardware and execute it and provide the response back to you. We are getting into an era where we're going to see in the near future, we're going to have a combination of a quantum and the classical computers are going to live together. Now, the classical computers has its own classical compilers. Similarly, the quantum computers comes with should come with its own classic quantum compilers, where all the high level languages that you are currently working on depend on what type of activity that you are doing. The actual execution will happen there. If you are writing your program for your classical computer, the execution will happen basically on the classical computer's hardware. If you're writing for quantum computers, then the execution could happen on the quantum computers as such, so that you can utilize the power of quantum computers as part of your actual day-to-day process as such. We are not at there, and that is where we see that we are moving towards. So that is what is depicted here, the future of your quantum plus classical computer. The reason behind it is the quantum computers requires a special type of environment, and it would be difficult unless there is a good number of research is being done to actually reduce the actual time required to actually, or the temperature required to actually get the superposition state and so on and so forth, so that we can have these quantum chips to be used as part of your regular computers. Until unless we get there, it is a long way ahead. It's all in the research as such. Until then, both quantum and classical computers are going to live together in the way that we have represented here. How it is going to do, that is what we're going to see. How the classical and the quantum computers are going to talk to each other and get the data or get the details that is required. Okay. So to do that, we should first understand how the current quantum computers are actually working. The current quantum computers, how are they actually currently working? So this is what is defined in this. For example, you have a problem statement that you wanted to solve using your quantum computer. The first step is in terms of building a quantum algorithm, and you will build that quantum algorithm, and the quantum algorithm will be converted into something called quantum circuits. So this is an example circuit that you are seeing here. So these circuits will help manipulate the qubits that you have created as such. Qubits that you have created. And these quantum circuit, you will give it to the quantum compilers, and the quantum compiler can utilize the either the original quantum machines for processing it, or you could utilize a quantum simulator for processing it. So what is the simulator? What is this quantum circuit? We don't know anything about it. We will see them in practical. Don't worry if you don't understand any of this. Those who have worked on, say, mobile application development and all, before you deploy your mobile application into your actual device and test it, what you can use is something called the simulators or emulators. These simulators help to provide a actual devices detail as part of your own machine, and you can actually enjoy accessing this simulator and test your program directly on the simulator before you actually go and deploy that on the real machine and test it. It is exactly the same concept here. Before you actually choose a quantum computer to execute your program, all the frameworks that we looked at provide quantum simulators. You can actually develop your algorithms and directly test it on the simulator before we go and deploy the details on the actual device and test it. So this is also we're going to see how we are going to deploy our code into a simulator and get it verified as well. Okay, so I hope it is clear in terms of how a typical quantum computing workflow happens. You define a problem, you create an algorithm for that, and you for the algorithm to execute that algorithm you need to create a circuit. Right now we don't know anything about it, how to create the circuit and all. We will cover them shortly, but don't worry about it. So once the circuit is created, you basically give it to a compiler. Compiler helps you execute this program on a simulator or a quantum processor. So that is what happens there. So now this is an example of uh, how a random number is generated. This is a circuit. To give you an example, we all are used to write our program for random number generation, and this random number generation, this is a circuit that is going to help you do the random number generation. It may look Greek and Latin, it is very simple, don't worry about it. We will see how to actually create our circuits shortly. Okay, this is just to give you an example of how the circuit actually looks. Okay. So now, how do we actually interact with the quantum computers? So the quantum computers, we know that we cannot hold it on our house. We may require a special environment for us to actually have the quantum computer in place. And because of that, there should be a special process to actually interact with the quantum computers. So you basically, from your classical computer, you provide the details that is required. The input could be an algorithm, input could be a data, input could be anything that you provide to the quantum computer. The quantum computer will process this information and it will provide the response. And the response, you will read it on the classical computer, interpret it, and visualize that on the classical computers. It's as simple as that. It is like you have a you have a cloud machine that you have created, you wanted to access. And how will you do? You basically access the cloud machine from your laptop and utilize that cloud machine to perform some operation. Once that operation is done, you basically complete and get that response, whatever the output that you're looking at, back to your local machine for your processing. That is exactly is what is depicted here in the quantum computers as well, right? So how, what is that we're going to do, how we are going to actually interact with the quantum computers? I've clearly provided the steps. Now here, what are all the things that you will do in the classical computers, and what are all the things that you can do in the quantum computer right now, and so on and so forth is defined here. In the classical computers, you can define the algorithm and convert these algorithms to a circuit, and from the circuit you send it to the quantum computer for execution. You can send it to a quantum computer, or you can send it to a simulator for execution. Once that is done, you need to read the result from the quantum computer, and the results are basically transferred to your classical computer for providing the response. Hope it makes sense. The reason why we are saying reading the response from the quantum computer, because the quantum the actual the quantum computers, the qubits are going to be in a superposition state, and the state pretty much varies every second or every milli microsecond. Okay, so at any point in time, whatever that value that you are reading, again if you go back and read the data, you may not be able to get the same output that you are looking at. That's the beauty of quantum computer. Okay, we will see how we can actually get proper outcome from a quantum computers and so on and so forth when we are doing the practicals as such. So let me start introducing our so now till now we have looked at what is a quantum computers and how the quantum computers basically help us in terms of executing uh, uh, our programs and so on and so forth. We looked at something called circuits and so on and so forth. Now let me introduce the framework that is going to help us do the actual process. So for the next 5-10 minutes, we will have the theoretical session, and then I will directly take you to the practical part of how to do things there. Okay. So now let me introduce the Cirq. Cirq is an open source framework for your quantum algorithm creation. It is available on GitHub, and you can go ahead and get the details on the link that is shared. The actual programming language that you will use is Python, is the programming language for interacting with it. Basically, the Cirq will help you create qubits, gates, operations, circuits, moments, and also apply simulation or on the real device execution and visualize the result. This is exactly what we are going to see in, in the next 1 hour, where you can use the Cirq framework to actually create the qubits, gates, operations, circuits, moments, and apply simulation and get the result from a real device, real quantum computer device as well. So this is what we're going to see on today's session. So now, before we get in there, we need to understand a little bit more about how does this qubit actually work. We know the fact that your classical bit can have only either of two values, either or 0 or 1. The qubits are not as such a basic single bit, in the sense the qubits are going to be a complex number, and the complex number is going to be represented by something called a ket notation. Okay, the ket notation is represented something like this. You will have a line, and you will have a arrow like this. So if you have 0, it is called 0 ket. If you have a 1, it is called 1 ket. There is also another notation which is basically like this, which is a bra, which is called bra notation. If you have 0, it is a 0 bra, and if you have 1, it is 1 bra. So effectively, for quantum computing specific activities, we will be, for mathematical representation, we will be representing them using bra and ket. We will focus on ket for now. The ket is the important representation for representing the qubit as such. Okay, so this is nothing but a 0 qubit, and this is nothing but a 1 qubit. Okay, so now this qubits, as we said, is on a superposition state. Assuming that you have a qubit and this particular qubit which is at this particular state, which at this particular state, if this qubit reaches this one, that is called excited state. If this qubit reaches 0 ket, that is called ground state. If this qubit reaches the 1 ket, that is called excited state. If it reaches the 0 ket, it is called ground state. So between these two, in the sphere, basically the value can be anything. So the quantum calculation for actually achieving that is using this formula. So let's see a little bit more about it. This is called a Bloch sphere. The Bloch sphere is where you have this ground state and excited state of your qubit, and the intermediate state is going to represent the actual value of the qubit that you are planning to measure. Think of this as you tossed a coin, and the coin could be, once the coin reaches your hand, the coin could be head or tails. But when it is in the flow, when it is in the air, it could be 1 or 0, or it could be anything in between, right? It could be changing from 1 to 0, or it could be changing from 0 to 1. So that is exactly what is being represented as intermediate state. So effectively the qubits are going to have, the value of the qubit are going to be having a probability value between 0 and 1. 0 1 1 ket here, that is what is represented here. So it is an intermediary state, that is what we are actually calculating as part of our quantum machine learning as such. Okay, so now here is an example of um, the actual qubits as such. And the qubit, the 0 ket, is represented with something called 1 0 matrix, and the 1 ket is represented with 0 1 matrix. And all that we will be interacting with is something called a state vector. Consider this as your 12th grade matrix that you have done. We're not going to look at the mathematical part of your quantum computer today, but of programming part. So these are some of the basics that would require you to understand even the basics of your programming as well. The state vector as such, you think of this as a matrix that you got. Okay, um, so this is a vector that belongs to a complex vector space. Assuming this Bloch sphere, your quantum bit could be at any place on this Bloch sphere. That is what is represented by the state vector. The state of the particular system at any point, any particular space on the Bloch sphere, is what is represented by state vector. Okay, don't worry if you don't understand. So we will get them clarified in the programming part. Okay, so now the next important concept you understand before we actually jump into the programming part is a quantum entanglement. So the quantum entanglement is actual property of a quantum qubit. What is this entanglement talks about is, if you have two qubits which are entangled together, if you read or if you measure one qubit value, you automatically know what would be the value of the other qubit. Okay, to simplify the whole thing, let's say you have a box, you have a hand gloves, you kept both the hand gloves on this box. The hand gloves, one is a left hand gloves, another one is right hand gloves. You know which one is for what. You kept it on a box. Now assuming that you are opening the box and taking one hand glove, that you got a left hand glove. Now you have taken out only one hand glove, but you know for sure what is that is available inside the box. You know that you already got the left hand glove, so obviously the other item which is in the box is a right hand glove. So that is exactly the concept of quantum entanglement. So there is a gate that we're going to look at. So don't worry about this gate. We're going to program it. C naught gate will help you do the quantum entanglement as such. Okay. So that is in terms of quantum entanglement. Let's look at the initial practicals in terms of probably let me just have this intro and then we'll go to the practical part. Let's start programming our qubits. We are talking about qubits. How do we actually start programming our qubits? There are three basic type of qubits that you can create in Cirq framework. The first is called named qubit, second is line qubit, the third is grid qubit. The named qubit, as it says, you're going to provide a specific name for the qubit. The line qubit, you won't specify a name, but you specify how many lines that you want for the qubit, and that will be represented in the circuit. And the grid qubit, as such, is to represent a grid representation of the qubit. If grid qubit of 4 by 5, that would say the fourth 4 comma 5 fifth position of that particular grid is what is represented by grid qubit. You can create say a 2 by 2 matrix grid as well as part of your grid qubit as well. There are three type of qubits: named, line, and grid qubits. Now let's go to the practical, the first practical. Let's see how do we actually create the qubits. Okay. So the instruction for which IPython library that you need to use is provided here. The actual source code is already provided here, and I would request you to actually download them and use them as part of your actual program as such. So I'm going to skip this. I will just end this. I will go to the programming part. So this is the actual IPython library. We're going to use Google Colab for all our implementation, and Google Colab allows you to actually directly execute these programs and utilize them as part of your delivery as such. I hope all of you were able to download the source code, and as it is available in the instruction, I will just show the instruction again. So as it is in the instruction, you can actually download, and in the Google Colab you can upload the first uh, introduction to Cirq Python IPython notebook, and make sure that you have I hope you are all able to see the screen. Now make sure on the right side that your actual notebook is connected state. Okay, so I'm just going to do a reconnect. When I do a reconnect, it will allocate something, some memory, and it will provide the details. Wonderful, yeah. So it is initializing, it is connected. In the interest of I have already executed this notebook. In the interest of everyone, I will re-execute it so that you will understand it, because all these are going to take a little bit time for me. Okay, so the first step is installing our package Cirq framework on the notebook, And the way to execute this command is either you can press in the Google Notebook the run command, or you can do shift enter if you are using Mac or Windows machine. So now it is executing. This will basically install the Cirq as such framework, and we're going to. I will just increase the font so that you are able to enjoy what we are planning to do. So this will basically install the Cirq as such. Right. So at the end of this, you have an option of restart runtime. If you restart runtime, then only your actual thing will work okay. Sometime if you're not restarting, you will not be able to get some of the details that are happening there. So I've just restarted the runtime, so it has restarted successfully. At the end, you can see that restart runtime. That will help you just restart the runtime so that it is working fine. So the next immediate step is importing our Cirq as part of our our coding, and we have imported successfully. And here is where we are creating our qubits. The first is named qubit. We talked about the three type of qubits. One is named qubit, and I'm just giving a name source, and I'm giving a name target. So these qubits I'm assigning to say q0, q1, and this is how you create a named qubit. Similarly, a line qubit, three that you have represent, and so it represents three q3 that you are creating there. Assuming that you want to create three different qubit using line qubit, you do that as well with dot range. And when you are providing dot range of three or four, whatever, and based on which your q0 will have a line qubit of 0, and q1 will have line qubit of 1, q2 will have line qubit of 2. And this is in terms of line qubit. And grid qubit as such will represent a specific grid. The position is 4 comma 5 in a grid. You can consider that as a matrix. In a matrix, 4 comma 5 is the location on which you wanted to have this qubit to be created. Why are we talking about this 4 comma 5? I will explain to you shortly. So this is a qubit that you created on 4 comma 5. Or you have an option of creating four different qubit with option of grid qubit dot square. This will create 0 comma 0, 1 comma 1, 2 comma 2, 3 comma 3. Four different bits, that is matrix, will get created using uh, using this particular square qubit. Okay, so to represent this grid qubit, I was telling you why this 4 comma 5 we are representing a specific one. To explain the details, I'm going to show you what is called our sycamore device. So you have Cirq underscore Google, which is part of your Cirq. And once you install the Cirq as such, it is also installed automatically. And when I execute uh, this particular statement of sycamore, that represents the actual device, sycamore device, how that is displayed, how that is configured, that is represented here. So if I want a specific qubit, for example 3 comma 4 as a qubit, all these are representing individual qubits on the sycamore chip as such. What you are seeing is the real device, and the real device you are actually seeing the actual actual sycamore chips position of different qubits as such. The reason why Google provides this information is there are very many nitty gritty information that if you have an entangled qubits, for example, entangled qubit is nothing but two qubits are connected together. If you have such an entangled qubits, when you are executing on a device, you cannot have these entangled qubits to be near to each other. These are some of the actual details that is being provided here. That is the reason that this information is provided here. So when you are designing your circuits and when you are designing your qubits, you can actually create them based on, without this entanglement or without this qubits being available near to each other, you can actually build the whole system. So that is the purpose of they providing the sycamores the complete device structure as such. Okay. So now going back to the presentation. Okay, now we just created a qubit, but we did not do anything on
Excuse
the
me,
qubit.
Prasanna.
Yeah, yeah.
Is it a Sycamore is the chip which the Google
Yes.
is trying
Yes.
to
Sycamore
create,
is
you think?
exactly. Sycamore is the actual
Uh,
device that is being provided. The structure that I
okay.
showed is the actual structure of the Sycamore's qubit structure
Mhm.
of the Sycamore chip as such. So in the Sycamore, this is how the qubits are actually represented. Okay, this is how qubits are represented. So if I want to utilize this particular qubit, then when I'm creating the grid qubit, I have to mention that 5 comma 4 so that this qubit will be utilized for your operation as such. We will see that shortly. How do we actually utilize them and so on and so forth. Okay.
Thank you.
Yeah. So we have created our qubit, but we have not done anything. We just created our qubit. In shortly, we will see some specific, way that how we can actually utilize the qubit. So the next is an important thing in terms of circuits. So, so a circuit is uh, an important. A circuit is a collection of moments. Let's first see what is a moment. Okay, let's say you have this qubit. We are going to do this whole from left to right. Okay, the whole thing that you are seeing is called a circuit, and the circuit has individual moments. The individual moments that you can consider or compare it with individual steps that your qubit goes through. Your qubit starts from here, and at this point in time you do some operation on this qubit, then this particular qubit goes to here. Now here, whatever happens, this is considered as one moment in the actual whole circuit. And again the same qubit is applied with some operation here and it goes to the next step, and this is another moment, and this is another moment. The moment that you are seeing, it does not mean that each and every operation that is happening is considered as moment. There could be a case where you have two three operations can happen at a parallel, and that can also be considered as moment. Now in this diagram, what you have is there is an operation being applied at that particular point in time on the qubit, and that is what is represented as moment. There could be a case, for example, here I'm just taking it as an example. The both of these set of operations, both this transformation on the qubits can also be considered as moments. So the circuit are considered as a collection of moment, and a moment is considered as a collection of operations. Here all these different, for example, in this moment we have three different operations that are happening in the qubit as such. There are three different operations that are happening in the actual qubit. The operation is an effect that operate on the specific subset of qubits. It could be a single qubit or it could be a multiple qubit on which the operation is done. To give you an example, when the qubit started, here in this case, this is one qubit, this is another qubit. Now on the first qubit, there is some operation is done. On the second qubit, there is some operation is done on the first moment. And then here is another operation in this moment where both these qubits are combined together. So that means there is an entanglement is being created between these two qubits. If you don't understand anything, don't worry about it. Just see and understand that there are circuits. That's the overall end-to-end flow of your qubit. That's a circuit, and within this circuit you have moments, like when the qubit goes from one state to another state, that is called moments. And to enable the moments to happen, you have something called operations that is being applied there. And these operations basically are applied on the qubits. It could be a single qubit or multiple qubits where you will be applying the operations. We will see now on what is this operations, what is this moment cube and circuit as such. So before that, we all are familiar in our our college times or even before that, to actually enable any bit specific operation in a classical computer. What is that you used? So I want to manipulate a bit. So how do you manipulate the bit? Any idea? Anybody can provide it in the chat. In a classical computer, you are all aware of bits, and I want to manipulate the bits, right? How do you manipulate the bits? Manipulate in the sense you modify the value, or you actually look at, yeah, exactly. You have something called gates, right? You're exactly correct. The gates, Shankar. So similarly, to manipulate the qubits, we have certain number of gates, and these gates will perform some operations. So the operations that we are looking at here were actually executed by some of the gates that are defined, that using that you will actually do that operation. So here is an example of a sample circuit and how the operations are applied on the actual quantum bits, qubits. Okay. Now here, let's take this one. Here there is a H gate, and there is a Z gate, and there is another H gate, and here is something called a X gate. Okay. So what is this H Z? We don't know anything about it. We will see them shortly. The H gate is nothing but is called Hadamard gate. The Hadamard gate is used to take your quantum uh, quantum qubit to a superposition state. The Hadamard gate is to take your qubit to a superposition state. That is what is Hadamard gate. And Z gate is basically to actually rotate your qubit on the Z axis. This is what you can see here. So Z axis, if you want to rotate, that is what is done by using Z gate. And H gate again is used for taking your qubit to superposition. So why are we doing this H gate, taking that to a superposition? Why are we doing this multiple time? So the qubits, as we said, has to be in a superposition state so that we can actually measure the value of out of this qubits. Measure the value out of this qubit. So that is what we are trying to do, and to get that qubit to a specific 0 or 1 state, the superposition state, that we are going to use the Hadamard gate as such. So here we are seeing X gate. X gate is to rotate that particular qubit on an x-axis. That is what is done using X gate. So don't worry about it if you are not understanding. So you will get it clarified as we progress there. Okay. So now let's look at the gates. So we saw a concept called entanglement. Entanglement is nothing but connecting two qubits together, so that if you read the value of one qubit, you already know the value of other qubit. Entanglement. There is a gate called C naught gate, and this C naught gate is able to provide the entanglement of two qubits. And there is something called Hadamard gate, which is represented by dot H, and that is used to take your qubit to a superposition state. And there is X gate, Y gate, and Z gate, right? And these are gates. And let's look at some of the operations that you can do as part of this gate. For example, if I wanted to do a square root calculation,
Now, if you don't,
so,
more question.
yeah, yeah, yeah,
Yeah. Already we with a H gate we are able to make the qubit at a superposition. That's where
yeah,
we need the value. Why do you
not
need
necessarily.
again Z again to
Yeah, that is to actually taking that to a superposition might not be the only thing that is required. So
Mhm.
as part of your algorithm, let's say you have a formula that you have created that you wanted to implement that as an algorithm as part of the whole solution. So to implement that, you may have to go through a certain number of steps to actually achieve that. Okay, so that is what is done using the actual Z gate, X gate, and Y gate, and so on and so forth. So there are a list of over, 100 plus gates which are already been defined and available as part of your actual program, and using them you can create your own algorithms and start utilizing the value out of it. So it is, you can consider this as you have one qubit. Okay, so only with one qubit taking it to a superposition is one activity, but that is not going to give you any meaningful outcome that you are expecting. Probably you may want to do some complex operation on that particular qubit, or a combination of 30, 40 qubits to actually achieve something well. So you consider this as your, if you want to have some kind of a programming construct that you wanted to do, how your assembly language actually executes them on a bit level. You wanted to implement, say a looping concept, a for loop on your program, at on a classical computer. You may be writing your for statement in your classical computer, but what happens internally at the bit level, we are not bothered about it, right, in a classical computer. But what happens in the quantum computer is that we are at the very initial stage of programming. Effectively you are programming at the qubits level. So you have to manipulate this qubit, you have to write the actual assembly language that this qubit has to follow, so that it can actually achieve the for loop that you defined in the programming language. So you cannot achieve
Okay,
that
can I
with,
consider,
yeah,
sir, the Z
yeah,
axis position which we are trying to make it
right.
is sustaining a superposition?
It will not effectively, because whenever you touch that particular qubit, one other property is that whenever, let's say, a qubit is there and you are taking it to a superposition state, and assuming that you are reading that value out of this qubit, as soon as you read the value out of the qubit, the the qubit goes back to its ground state. Think of this way, that you have one qubit which is available and providing some value to you, and as soon as you read the value out of it, or you do some operation out of it, it goes back to your ground state as such. It does not provide you any other value as such. So this is also another property that you need to think of when you are building this algorithm as such. Okay, so for each and every operation that you are doing, you may have to actually see how you can effectively uh, utilize the properties of this qubits and build your outcome that you are expecting there.
Okay, thanks.
Okay, yeah. So we will write some circuits, and at that time you will understand what is going on. Okay, so we will execute it on the simulators and the devices as well. You will understand what is going to happen there as such. Okay, so here is how you actually do a square root calculation, and also here is how you actually do say you know power gate. You want to do on the y gate, you wanted to do an exponent of 0.25. That also can be done by using the operation. So these are some of the gates and the operations that we looked at. And before I go into probably I'll just explain the circuit as well, and then we can actually see directly the demo of the things. Okay, so now then next is how do we create the circuits. We talked about the circuit, how the circuit combines your qubits, your operations and the gates and so on and so forth. This is how you do it, and you create the circuit using circ.circuit, and you use the append operation for adding some details as part of your circuit, and to run your circuit, there is a default simulator that is being provided part of Cirq, and we can utilize that simulator to run and see how the response is going to come. The simulator.run is going to provide the actual response for you. Okay, let me just go back to the code and show you how the actual simulator works, and then how the circuit is actually created. We looked at here in the same page that we have taken. Here is an example of different gates. So here what I'm doing is Cirq provides something called dot c naught. We talked about it. This is to actually create an entanglement between two different qubit. It provides an option of you moving this particular to any particular custom name that you are creating. This is a default value circ.c0. I'm creating a new name for this c0 gate. Circ.z is poly z. I can put my own name for that particular gate as such. And how you basically do a square root, for example, on the x gate, I'm doing a square root using the calculation. The whole thing that I'm moving into a variable called square root of x gate, and y to the power we just saw, and I'm moving this exponent value to my variable here. Now, till now, these are some of the operations. Let's say I'm creating a line qubit. The line qubit we just saw with the range of 2 that represent 2 qubits will get created. I'm going to name these qubits as q0, q1. Excuse me. Q0, q1. Now, I can apply different operations on these qubits like this. Now, for example, I applied the circ.z. I am applying the z gate on the q0 qubit, and I'm applying the c naught on the q0 and q1. The c naught is basically for entangling these q0 and q1, and this outcome is stored in the not operation. Similarly, I wanted to perform a swap operation and a square root operation on the swapped value. I can perform it as well by using this square root underscore I swap on the Cirq, and I can save this q0 and q1 value in this particular example as such. Okay, now you can use this custom names that you have created for applying on the qubits as well. For example, here this is a C naught operation that I have created a new name, and that I'm using here, and representing Q0 and Q1 as the qubit. On that, I'm applying the C naught gate. Similarly, the poly gate I'm applying here, and all the custom names that I have created, for example, square root X gate, I'm using here, square root Y gate. So this is how you basically create the operation. I can just run this and this executed perfectly. Now comes circuit. So we talked about circuit. The circuit contains qubits and the operations that will be applied on the qubits as such. Okay. How do we define the circuit? I'm just taking this circuit equal to circ.circuit. So this, I have created the circuit, my first circuit. In this, I need to define how many qubits I wanted to see. I'm defining a line qubit. You can define anything. You can define named qubit. We will see as we go how it happens, that we will see. So now we have created two qubits, q0, q1. Now, and once I create the qubit, I can apply some operation on these qubit using gates. We talked about gates. H is used for Hadamard gate. C naught is for entanglement of the details there. So now I'm creating these H gate and C naught gate and appending as part of the circuit. So this is the first append that I did. Now I'm also planning to do something called a measure on this particular Q0 and Q1 qubits. The measure basically is to actually get the output out of this qubits. Okay, I appended this. Let me just run this, and let me just run this. Now if I print this circuit, now you can see that I have a 0 and 1, q0, q1. This is the two lines that are created. So what I have done is, on the q0 I have applied a Hadamard gate that is represented here, and on the q0 and q1 there is a C naught. You can see by using this connection between these two, that represents these two qubits are connected, and these two qubits are applied with the C naught gate, and we are doing a measurement separately for q0 and q1. So I'm doing a measurement on q0 and q1. Okay, so this is how you create your circuits. So now we have successfully created our qubits. We have applied some operations on these qubits, and we created our circuit and added these circuit operations into that particular circuit, and we are visualizing these information in this in this way as well. Okay, so any question till now before we go there? So we just created the circuit that we are talking about. In the presentation, we said anything that we wanted to do, we need to create a circuit before we actually move on to the next stage, right? Okay.
Which is the
So
blueprint
what?
part of this circuit?
Yeah,
Yeah, over to you, my friend.
please.
Yeah. So I
Someone is
mean,
asking, please
when
continue.
yeah, yeah, yeah. The circ before movement is the when you say Edamar gate, is that the initial position for the qubit, or does
So the
once you
Yeah, so the qubit, what is the initial position? We don't know. Okay, so that nobody knows. It is not like, you allocate some value for a variable that we are doing here. Not like that. So effectively, the Hadamard gate basically takes this particular qubit to a superposition state. So that is what it does. Now, initial value could be anything. So that's where we are talking about. The quantum computers have a huge amount of error rate, because the value that it is going to have, it is going to have, different values. Typically it could be at the ground level. So all the qubits will be at the ground level. That means it would be effectively zero. It would be effectively zero. And as you apply multiple gates, it takes multiple values, multiple different turns, and multiple different values as such. That's the assumption that with which we need to work on.
Okay, so the Adamor gate takes to a superposition which
Correct.
can be a 0 or 1, or it's 1.
It can be anything in between as well. So you remember that, it is a coin tossing stage. So compare the superposition state as coin tossing stage. You have
Yeah,
50% probability that it can be 0, 50% probability that it can be 1. So we never know.
yeah.
And when you calculate that particular value, when you actually measure the actual value, that whatever it gives is the actual value. Hope it clarifies.
The last point is, but a superposition will be either 0 or 1. That is confirmed.
Yes, it is not
Yeah.
either. It could be anything in between as well.
Yeah,
So it is not the 0 or 1 or anything. It could be in between as well.
no, we said in the superposition means it's not in between. It's the this one, correct? In the in between would not be superposition, correct? That's what my understanding. Maybe I'm wrong. Yes.
Superposition is considered that, um, just to give you a simple analogy, you have a coin on your hand. When you have a coin on your hand, you know exactly whether it is head or tail. Let's say when you are tossing your coin, when the coin is tossed in the air, it is going to be in the air. It is going to be still rotating. And can you guess what would be the value of it? Nobody can guess, right? It can be 0 or it can be 1. It can be anything in between as well. So that is the level called superposition as such. Okay. So the value, if you go back to the actual presentation in terms of how the Bloch sphere actually works. So here, this is this is a qubit. The value of the qubit is defined based on what is the probability of the 0 state and probability of the 1 state and anything in between that. So it is an intermediary state in between that. That is what could be the superposition of it. Hope it makes sense, right?
Yes, it clarifies. Thanks.
Yeah, sure. Yamali.
In the code, can we think
Hmm.
that whatever there in the append block, can
Yeah.
we consider that is as a movement?
No, not necessarily. I will show the difference shortly. Okay.
Yeah.
So now here we printed the circuit, and
Mm-hmm.
uh, and now let us simulate this particular. The next step is, once we completed our circuit, we need to actually run it, right? So this is like you created your mobile application, you coded it. You need to run it to see whether it is working or not. Or
Mm.
in the case of web application, you created your code on your local, and you need to put it on the server to see whether it is displaying properly or not. It is similar to that. So the next step is you need a simulator to actually simulate and see how it works, right? So that is where the simulate Cirq provides the default simulator. And when I use this default simulator, I'm going to define that as a sim. And you basically give a circuit and tell how many times that you wanted to run, and you can specify the detail, and it will run for that many number of time, and the result will be taken, and you can actually uh, take and print the result of the actual simulation as such. Okay. So now if I run this and I print the result, the value of q0 and q1, that you can actually see here what is happening here. Okay, so that is what is represented here for 10 times run that has happened here. Okay, so now your question is on the moment. Okay, so I don't know whether I had the slide for a moment. One second, let me just see. Yeah. So
Prasanna, Surya here. I have one small question.
yes, yes, Ria.
Actually, here we are dealing with all zeros and ones, right? So
Correct.
let's say we did something wrong in writing that particular code, and
Right.
how do we identify the runtime? errors actually, something like
Uh,
logical errors or runtime.
right. And the so effectively here, from the programming point of view, the execution is going to be step by step. If you want to execute it all together, it is fine from the Cirq programming. See, here is a program that you have written, and you can actually execute it one by one, right? You're talking in terms of collab as such, or from the quantum computer point of view.
My question is, here the answer is something like in
Yes.
a
Yeah.
bits, right? Zero, one,
Right.
something like that.
Right.
So my question is, let's say we did something wrong and we did not get the expected result. So how do
Okay.
we know? That's what is my question.
Okay, so there are testing frameworks are available, and there are error correction frameworks are available as part of Cirq itself, and that we can cover as part of our advanced session. So basically, it is like a complete end-to-end framework in terms of how you actually interact and work with the quantum machine learning as such. Okay, so there are a lot more is available. What we are touching is like a hello world applications. What we are talking is only hello world application. Yes, how do you actually debug as such? We cannot actually debug it, but we can see how when you are performing the gates operation, how your gate operations is progressing, intermittent values that you wanted to measure and see, those measured values are possible. To give you another thing is, for example, one other option is in terms of measure. So these measure is like your print statement on your program on what is the value at that particular point in time. So that is what you can have this at any point in time part of your program, the circuit design as such. Okay, so that will help you get and see. It's like a print statement. It will give you what is the value at that particular stage, something like that. Hope it makes sense,
Yeah, got it, Prasanna. Thank you.
right? But that is not. This is like a print statement, but there is a detailed, not a debugging tool or something like that, but a detailed, error handling options, and also program execution options are available as part of Cirq. So yeah,
Sir, also I have a question.
yeah,
Uh, Previously, we did entanglement on Q1 and Q0, right?
that is right. Yeah.
I thought maybe I'm wrong also about this point, but I thought entanglement means that Q1 and 0 will have same value. Is that right, or my understanding is wrong?
Q0 and Q1 will have the same value.
Yes, if you did entanglement.
Yes, that is correct. Yes,
Ah, okay, that's why they have same value here, right?
that is right. Yes.
Oh, okay.
Okay.
Yeah, yeah. Actually, I was just doubting myself. I thought I read the number wrong, but they are equal actually.
Yep. Yep. Okay. So, any other question? Okay. So now,
Yeah, so sorry.
yeah,
So I mean, when they are going to say already you asked when they are going to have the same value, I mean, what is our purpose of creating an entanglement? Is it to verify the results, or is it? I mean, do we require to do that?
we need multiple qubits to act, in the same way, and we can utilize the entanglement as a property to actually do that.
No, I mean, any specific reason? Because one qubit I'm going to do the processing. Why do I need multiple qubits to do the same thing? Just that's
We,
the
we,
confusion.
we will see some more examples so that you will understand the details. Okay, no worries.
Yeah, thanks.
Sure. So now, the question from Mali is in terms of how do we consider moments? Should we consider moments as each and every operations as such? Okay, so that let's create a different circuit. And here, what I'm doing is, for example, I define two qubits. I'm going to use a different way. Now I'm going to define the qubits as named qubit. So now I'm defining A and B as two qubits. I'm creating a circuit, and now in the circuit, and I'm going to apply Hadamard on A and C naught on A and B and measure on A and B. So let me just run the circuit, and now I print the circuit here. Okay, to see the movements in the actual, what is happening here. Now I can use a loop to actually get what happened, what is the moments that is happening here. This is a code to actually understand how the moments are happening. Now here the first one is moment 0, Hadamard gate is applied. In the moment 1, the actual C naught gate is applied, and in the moment 2 you can very well see that the measure part is happening here, right? Now the same circuit I'm going to actually tweak it little bit. Tweak it little bit. So now here what I'm going to do is, and also apart from moments, you also have something called a representation of a circuit. Using the representation of a circuit, you can actually display the details like this. Like what happens in the moment, the details can be displayed like this as well. Okay, so now in the simulator, I'm just going to put it through the simulator, the the actual gates, and run this particular details on the simulator. Let me just run it. Let me define this as a first simulator, and 10 times I'm just printing the details exactly as it is. Now I'm going to do a small modification in the circuit as such. So the modification is the X gate that I'm going to include, sorry, X gate I'm going to include as part of my circuit. So now just to compare, so here previously I had Hadamard, C naught and measure. Now after Hadamard, now here what I'm doing is I'm adding Hadamard X gate on the B and C naught on A and B and measure the values there. Okay, X gate is means the or bitwise uh, shift is what is done. Bitwise not operation you can consider in terms of the particular gate that you are looking at. Let me just define this circuit. Now I'm defining a different simulator. When I run this particular simulator and see the result, and now you can see that wherever the value is a and the value gets converted, value of a is 1, the value is getting converted into 0 on the result, because we have added the X gate as part of this whole operation as such, right? So that is what. Let me just try circuit 2 moments for the circuit 2. I don't have that here. Let me just add one. Print circuit 2. Okay, I think we need to print the moment, or I'll say representation. Now here, to answer the question, for example, on the first moment, that we can see that it has considered both Hadamard and the X-gate operation as part of the first moment. And in the second moment, the C naught gate is done. And the third moment is where the measure is done. So it is not that, the individual operations are considered as individual moment. There is a group of operation can be considered as a moment as well. So this is somewhat similar to our parallelism in as part of our programming that we used to do. Moments you can consider as a parallelism that we are actually doing there. Okay, so
It's
that,
like,
yeah,
sorry, sir. It's like
yes,
multi-threading. It's like
it is
running
like a
multi.
multi-thread. Yes, that is exactly correct. Yeah, that is right. So that gives the basic. Now till now what we have done is we have created a circuit, created a qubit, created various things that is required, and basically integrated everything and executed the circuit on the simulator and viewed the result there. Okay, that is what we have done. And now going back a bit on the presentation, the next item is advanced simulator. So um, Google also provides something called a QSIM, which is an advanced simulator for executing some of the advanced operation as part of your program as such. So the QSIM, you have to install it as a separate external simulator and have it used for your execution. It is like if you are doing mobile development, you have default simulator provided by Android and Google, Microsoft, and sorry, Apple. But you want to use a different third-party simulator, you have to install it. Something similar to that. The reason for using this is much advanced, and it can actually help in terms of debugging and also in terms of error correction as well. Many of the algorithms that development all happens using utilizing QSIM as part of their implementation. Now going back to the code, so how do we actually utilize that QSIM? You have to specially install it. So I have installed it. Now you can install and you can import the QSIM Cirq as the package, and use the package to actually run your circuits separately. Here in this case, you won't see a difference for a simple circuits, but you can do a lot of powerful operations using QSIM as such. So here is a different simulator. Cirq.simulator is the default simulator provided by Cirq, and this is the QSIM simulator that you have used for simulating the output. Now, both, if you look at the output level, based on the gates that you have given, it is absolutely the same. That the details, and I see a little different, and you see that there is 00, and here it shows 11. Let me just execute it again and see whether it is giving some kind of a difference in result. Okay, so I'm just here. Yeah, here also some difference that I'm seeing. So in terms of the input, as such, Hadamard value, we do a Hadamard gate and the next gate and CX gate, and CX gate, and you do a measurement on Q0 and measurement on Q1 that you are doing. So using a default simulator and you using a QSIM simulator, you get the output. And basically, I see a different Q0 is different and Q1 is also different that I'm seeing when we utilize the QSIM and the normal simulator that we are using here. Okay, so that is
Sir,
yeah.
sorry. Is that possible because we are looking at different moments? As
No,
you explained in the what you call it, the presentation,
right.
uh, the value is different every time you look to the Qubit.
Qubit, yes, true, and true that in terms of even if I execute this again, the value could be different. Whatever that we got could be different because the value that we will get at that particular point in time would be completely different. For example, now 10111 that I got, I execute it again. Probably I could be getting something else. See now 011110. So the qubit value has completely changed. asset. So this is an example of how when you put it into a superposition and try to read the value out of it and try to present, you get a different output at a different point in time. Yes.
Yes, so that's my point. That's, I think, why the normal simulator is different from the QSIM, because
Absolutely
we are
true.
reading. Yeah.
Yep. Yep. So that represents the introduction part. And what I'm going to do is do an advanced part. I'm going to keep the whole thing live. Wanted to discuss. Do you have any questions? We'll give 5 to 10 minutes break and then come back. We have a lot to cover in terms of advanced concept in the circuits, and how do we actually create TensorFlow machine learning, integrate them, and how do we actually use them for our implementation and so on and so forth. So any questions I can clarify, or I can give 5 to 10 minutes break. So now it is around 10:50. So 11 o'clock again, we can start to actually have our session continuous. Yep. Rejoin at 11 and it will be active. You don't need to quit or anything. You can just be active and you can take a break and come back. And I will keep this active. The same link. You don't need to exit or anything. You can come back. Yeah.
Just a quick question, sir. Will we be using our local device, like Visual Code or something, to try these
Uh,
codes?
it will be all directly on the Google Colab. Google Colab provides the option of directly executing it uh, with the devices and the simulators. And the option is, yes, you have an option of directly installing the Cirq as part of your Python option of your Microsoft code and all. You can have it configured and you can start writing it there as well. That is also possible. It is like your typical machine learning programming that you are using. So it is the same option that you will use for implementing. There's no
Ah,
difference.
okay. Because I'm facing a problem in installing Python in my laptop. That's why I'm asking.
Right.
Ah, okay, great. Okay, let's meet then.
Sure.
This conference will now be recorded.
Right. So hope you're able to see the screen.
Yes, Prasanna, you can see that.
Okay, great. Right. So so let's move on to a little bit advanced one in terms of we looked at how a gate gets utilized as part of our operation, as part of we creating our circuit and so on and so forth, right? So if we wish to actually create our own gate, how do we do that? So there are three basic premise in terms of creating our own gate as such. So there are three basic premise. One is in terms of you define how many qubits that you wanted to interact with, and you define something called a unitary matrix for your gate, and the actual circuit diagram information that you wanted to display for the gate. So that is the next thing that we're going to see, and we will see in the programmatic way how it is done. That is one. The next is, once you created a gate or once you created a circuit, how do we actually transfer these circuits from one location to another location? In the sense, right now you created a circuit and you wanted to share it with your friend. How do you do it? So Cirq provides something called to JSON and read JSON. It basically converts your circuit information into a JSON format, and you can export this JSON into a CSV or .json file and have that shared to anybody that you want. And if somebody else is sharing the circuit, you can actually import the circuit directly part of your code just by using read JSON. Similar to how you typically read a data for a machine learning project, you basically do that using to JSON and read JSON as such. So this is also we will see an example. And the next is in terms of device interaction. So till now what we have been talking about is in terms of executing it in the simulators, how we can actually connect to a device and how we can actually execute our circuit directly on the device. That's an interesting part. So this gives you a hello world of end to end of what is that you can do in terms of from basic circuit creation, and add your own operations, create your own gates, and apply the gates on the circuit, and have the whole circuit executed either on the simulator or on the direct device. That is what we're going to see now. um, so now within that sycamore execution, there are some of the construct. So circ google.sycamore command is used to get the device for us. Now how long it is going to take for us to actually execute the particular circuit, so that can be extracted from something called a gate duration. And we mentioned one thing in terms of when you have two entangled qubits, they cannot be near to each other, and if you have them, that is not acceptable in the quantum computers. Now this how do we validate in the device? And you can actually use something called validate operation that can actually help you identify is there any qubits which are entangled, which are near to each other. If that is there, then it can actually identify and provide you the details as well. So these are the things that we're going to see on the next practicals. Now to do this, I would request you guys to actually download the next file which is available on the GitHub, which is advanced circ with 2 is the number that you have to look for, and upload into the actual collab. Let me just go to the collab. Now here, this is the file which is already shared. Now this is the advanced circ 2, and here I will just check whether you have connected. If not, make sure that you are reconnecting to the uh, actual backend servers, and it is connected. Your RAM is allocated for us. Now you can actually execute the Cirq to actually install it. The problem here is each and every notebooks that you have, you may have to install it separately and have it executed. So you are installing that on the machine that you got from Google using Colab. And once the installation is done, you can actually start importing and start using the operations. So done. So right now, if it is asking for you to restart it, you can restart it. Otherwise, you don't need to restart the environment, because it knows if it has the details, it may not allow you to actually, may not require to restart the environment. So it has not asked for the restart environment. So I'm leaving it as it is. Now I'm just importing the Cirq, and it is imported. And NumPy is a Python library for your data processing and data manipulation. So you can use NumPy for building the matrices and so on and so forth, and working on matrices. So that is what we're going to do. So the first case that we have looked at is how do we create our own custom gate. So that we are going to look at. So I'm going to define a Python class called mygate, which is going to inherit the details from cirq.gate. Cirq.gate. So there are four different methods, and the first method is init. Simple super. You call the super classes my details, and pass on the mygate and self. And the second method is number of qubits. If you return one, that represents your gate is going to work with 1 qubit. If you take two, your gate is going to work with 2 qubits, and so on and so forth. Okay. And what is the operation that you are going to do is represented here. Now here it is a unitary operation that you are planning to do. There could be multiple different things that you wanted to do that can be represented here. Now for the data that is coming in, you are taking numpy.array, and there is an array of data that you are giving, and divided by np.square root of 2. So this is, I'll consider that some operation that you are planning to do on the unitary array, unitary matrix. So that you are doing it. And circuit diagram information, the third one, represents how your gate is going to be represented when it is in the circuit. So you represent the gate by a name called G. So now this is a simple class that you created. It's a custom gate of your own gate that you have created. Once the gate is created, you create an object for this particular gate. Now once the object is created, you can use this object for any of your circuit. Now let's take I create a circuit. Now in the circuit, I am using this gate on. Now if you look at, I've not created a separate qubit and all. I'm directly mentioning cirq.line qubit of 0. So directly applying this gate, you can do it separately as well. You create a qubit separately, create an operation separately, and apply that particular thing in the gate as well. That is also possible. Okay. So now print the circuit. Now you can see that the circuit is printed. There is a qubit 0, and that has been applied with a gate called mygate. The mygate is represented with a G. So that is what is displayed in the diagram here. So this you have completed creating your own gate, your own operation as part of your quantum computing as such. So you can use the same gate for your simulation as well. The same circuit, I'm putting it for the simulator, and when you simulate and get the result, it basically gives some output there. Okay, based on applying the details in the simulation as such. Okay. So this is an example of how do you actually create your own gate as part of quantum machine learning as such. So any question on this? Okay. So the next is we looked at how do we actually share the circuits that we have created. So there are two operations we talked about. You can actually do JSON to convert your circuit to a JSON file, and read JSON to actually read the JSON and import it part of it. So now here I'm defining a circuit, and this circuit will have Z gate, and also has a grid qubit of 1 comma 1, and that circuit I am converting into a JSON. I'm storing it as a JSON string. So this JSON string I'm printing. When I print this JSON string, I can just execute it again. So a JSON string, this is the JSON string. So effectively the qubit and the operation, everything will be converted into a JSON format. And here, to utilize that particular JSON string, I'm creating a new circuit with the JSON string that I've got, and importing, that is reading this particular JSON, so that the data from this JSON gets created in the actual circuit as such. So I can just print the new circuit. Actually, you can see that it is a new circuit that is getting printed here. So this is an option of you to import or export your circuit that you have created, so that you can do a reusability of the actual circuit as such. Very simple.
Uh,
Yeah.
yes, sir. I have a question. I just noticed. Is
Yes.
it possible to create our own gate based on
Yes.
already existing combination of gates? Let's say
Absolutely.
X.
Okay. Yes, you can do that. For example, here, in this example, what I'm using is the square root operation that I'm performing on this, and this is what will be applied. And when you are creating this gate, you can utilize the gate which is already available and use that to have your own operation that you wanted to perform. You can certainly do that. Yes.
So above this one, you can, for example, after this operation is done, I want, for example, to do a rotation. Let's say
Yeah.
X rotation
You can. You
above
can
this
do.
one.
Yeah. You can do everything. Yeah, you can do everything. In that case, what you need to do is you need to pass on some parameters, like for example, the qubit information has to come in here, and that qubit information you need to manipulate and do things, right? So we will see how we actually pass some parameter to a circuit shortly. Okay. And in the runtime you wanted to pass some parameter, how do you do it? That we will see. Yes, that is applicable for gates as well. Yes.
Okay, great. My second question, if possible, I noticed, sir, that you divided the code into multiple snippets.
Right.
Is it possible to create one snippet, one go later?
Absolutely possible. Absolutely possible. So this is for your understanding. This IPython notebook is created. You can have this all this information that I am putting together, and you can create a simple Python file and have it executed in a single go. It's all possible.
Okay, great, great. Thank you, sir.
Yeah. So we have looked at how do we create our own gate. We looked at how do we import and export the gates, circuits, and the next thing is the important part in terms of executing our circuits directly on the device as such. So the first is Google provides a very simple mechanism of actually accessing your device. Now Cirq Google.sycamore basically provides the Sycamore device for us. This is the qubit structure of the Sycamore device as such. And the first thing is how long it is going to take for us to actually run the operation as such. Here what I'm doing is, let's say I create a circuit with X gate on a circuit with a grid qubit of 5,5. So that should be represented here. So this would be the qubit that is getting created in this. And here I'm going to call this as some OP. And instead of directly running it on this in the actual simulator, now what I'm going to do is I'm going to take Cirq, Google, and Sycamore and metadata dot the get duration. I'm just storing it in the get duration file, get duration variable. And on this gate family, I'm just looping through to get this particular OP in the gate family, how long it is going to take. So if I run this particular item, so I think I need to import first. I need to import Cirq and then the Cirq.sycamore, and then how long it is going to take to reach is approximately 25 nanosecond for me to actually reach this particular qubit 5,5. So that is the duration that it takes for us to reach that particular gate there. So next important thing is validation on the device. We talked about when two qubits are in an entangled state, they cannot be near to each other. That is, two different entangled qubit cannot be near to each other. Two different entangled qubit cannot be near to each other. So that's a rule from a device point of view. So let's take, for example, 5,5, 5,6, 6,6. In this diagram, if you look at, so the 5,5, 5,6, and 6,6. So these two and this is the three qubits that we are going to define, the location that we are going to define in this whole in this particular qubits. So now if you look at, I'm going to create an operation, for example, square root of I swap, something that I'm performing on 5,5 and 5,6, and I'm performing a similar operation on 5,6 and 6,6, and I'm doing 5,5 and 5,6 and 5,6 and 6,6. Yeah, so I'm performing operation here this way, and I'm performing operation this way, that is 5,6 and 6,6. So now if I do this operation, and if I actually print the actual circuit, and we have an option called in the device a validate circuit, it will tell whether this particular circuit is valid or not. So that information can be verified here using this particular operation. So if I execute this, it will tell me that, so here is an iswap operation that you are doing, and here is another iswap operation that you are doing, as it is mentioned here. So it says that this qubit pairs are not valid. For example, 5,5 and 6,6, you cannot have these operations on this particular qubits at the same time on the same circuit as such. So like this, there are various rules when you try to execute them on the device that you may have to go through to understand more about how the qubit operations are actually executed on the device. Now we have successfully taken our circuit and executed our circuit on the device, as simple as writing a simple program. You are currently in the hand of a quantum computer, so you have access to the quantum computer as part of your execution as such. Okay, that is the beauty of simplicity that Cirq provides for you to actually access and utilize it. So right now what we are using is the Sycamore device that is provided by Google, and Google has an option of integrating with almost like 10 different players. Even Microsoft Cloud you can use. Microsoft Cloud provides an option of accessing Microsoft's quantum computer, and you can access that using Cirq. you want to deploy and see on their quantum computer how your circuit works, you can use and perform that directly using the same program as such. Okay, as simple as that. So they are actually creating a way that abstracting out all the other complexity and simplify, and as a programmer you focus only on things that you wanted. If you want to focus on algorithms or the things that you wanted to take it forward, you focus only on that. So that's the goal of it. So any question on this till now before we move on to the next one? So in this practicals, we looked at how do we actually create our own gate, how do we actually create export and import of your circuits, and how do we actually directly interact with the quantum computer and validate whether our circuit is valid or not directly from the quantum computer as such. So that is what we looked at in this one. Any questions? Great.
So when
Prasanna,
we create
axing.
our, yeah, when we,
Please go on. Yes, Surender, please.
okay, sorry, yeah,
Please go on.
okay. So when we create our own gate, okay,
Yeah.
I mean, like X or Z or this one, we do not know what is the axis of rotation or anything, or we can actually control those things also.
We can actually, the existing gates, the operations are already defined. What it will do, what kind of an impact it is going to do, it is already defined. So when you create your own gate, if you are planning to utilize the existing gates as part of your operations, then you need to understand it before you actually implement it as such. And yeah, there is like hundreds of gates which are already defined. Even there are a lot of custom gates are there, that's all being created as we speak. In the sense, like you and me, it's all open source project. You want to create your own gate and put it there as part of the Cirq, and you can do that. And it is just a matter of you checking out their code and create your own gate that for a specific problem, and you can upload it to the GitHub, and they will approve it to take it forward as such.
Yeah, that part I understand. My question is, I mean, I'm just trying to draw an analogy with what we know in the regular, normal computers we use.
Right.
Basically, even if I have to write a new assembly language thing, it's nothing but a combination of and or not gates.
Correct.
At the end of the
Correct.
day, I have to calculate what would be the output to this one. So, like this, there is a base gates whose combination I need to take. That's what I'm trying to understand.
Yeah, yeah. There's like hundreds of it available. That's what I'm saying. Yes, it is available, and it is
Okay.
in hundred, and you can very well utilize them for your own gate creation as well. Yes,
Okay. Thanks.
sure. So we have seen, say, swap and square root together. Actually, there is a swap gate separately available, and square root gate there is a separately available, and somebody combined these two together and brought swap with square root, something like that. So you can swap and do a square root on the actual value. So that is another gate that they have created, another operation that they have created. It is all possible. Yes, sure. Yeah, Mali, please.
Yes, Prasanna. So we are accessing the real device in the sense the
Right.
Google Sycamore chips we are trying to access through cloud. You mean to say?
That is correct. Yes.
Oh, okay.
So they
So
provided the interface. So you are importing and you are directly accessing the Sycamore device, and this is as if you are executing on the Sycamore device as such. And similar way, IBM provides their quantum computer access through Qiskit. Qiskit,
hmm,
using Qiskit, like what we have done with the Sycamore. Exactly, once you create, it is exactly, the process is exactly same for any framework that you take. The
hmm,
first step is you create a circuit. Even in IBM, you create a circuit in the Qiskit, and once you create the circuit, you deploy that circuit on the simulator for testing. Or you want the device, you have to actually import the corresponding library for device connection and push that circuit to the device and get the response from them. As simple as that.
Understand. So the whatever the like when we are trying to print the scheme or the gate, right? Complete thing.
Right.
So it is showing some type of architecture. Like it's not exactly a matrix, but somehow it is like.
Correct.
Is it the way they designed? You think of? I didn't get that one. That's just.
I have no idea why it was
Mm-hmm.
like this. That I understand. Even I have the questions. Why they have this structure? You see this matrix structure,
Yeah.
right? This
Right.
is a structure. I have no idea why that structure is like this.
Understand. Fine, Prasanna.
Yeah. So it may be that the chip when they have created, they wanted to place the qubits at this particular position, something like that. I don't know why. Okay.
Hmm.
Probably need
Fine,
to
Prasanna.
get more detail on that. Yeah.
Thank you.
Sure. Any other question?
Prasanna, yeah,
Yeah.
Prasanna, I have a question. This is Sudarshan.
Yes,
Um,
sir.
I'm not I'm not very well versed with assembly language and all.
Right.
The thing is, when we are trying to do a functional thing like our requirement of programming, right?
Right.
And these programs, we'll have a nested programs, right? A lot of programs within a program. Like right now,
Right.
what is happening with the Dockers, Kubernetes, and all this stuff,
Right.
maybe the same concept there. But when we seek the results from the processing,
Hmm.
if the speeds of the network and the cloud capability to cater to the speed of the computing, right? That's the thing that will not that will actually affect the way we are getting the results from the quantum computing. In the sense, computing may be very fast, processing will be very fast, but we cannot run all the program at one time within the quantum computing, right? We get results from the processing, and then we process that result and we put that into another program, and then that program will go back to processor, and it is a continuous effort in any laptop or anywhere, right?
You are
So in that
exactly
case,
correct.
yeah.
Yeah. Please go on.
So yeah. So how we are going to resolve this issue? Because even if it's extremely fast,
Right.
the storage, we
Right.
daily deal with the storage, right? That storage itself is a big hurdle as far as the computing is concerned, right? So how they are going to achieve these speeds of
Right. Right.
what quantum computing is? Thank you.
You're exactly right. And there are two ways that we can look at this one. One is in terms of the operations as such. Typically, when the operations are being executed here, how they are executed is in terms of circuits. So you want to perform multiple steps on the quantum computers. You create these multiple steps, multiple manipulations that you wanted to do as a circuit, and you actually give that to the quantum computer for processing. Okay, that is one way of doing it. So it is like combination of these steps which will get executed at the quantum computer. That is one. And the second is your point is absolutely valid in terms of we may require the data to come back. When it comes to machine learning, that is the case where
Right.
when you want to utilize say quantum neural network, so you wanted to actually understand what is the actual outcome, and based on the outcome, if you want to, for example, let's say you build a quantum neural network where in the first round of quantum execution you got some result, and when you compare this result with the actual result that you are expecting, there should be an error, and to correct this error you may have to adjust the weights and biases on the neural network. So when
Right.
you come back and do that, it will be a classical computer activity, not a quantum computer activity. So you adjust your weights and biases here and build your circuits and everything. Again, you push that back to your quantum computers for doing it. This is an active research, and still a lot more is going on. So that's where, if you look at, even though we are talking about thousands and thousands of qubits in the case of IBM, even for the device that we just talked about, Sycamore device from Google, they won't allow you to write any program more than 30 qubits in place at this point in time. If you want more than 30 qubits to be utilized, then you need to directly talk to Google to get a permission to actually do that. Even within that 30 qubit, there is a restrictions on how many operations and the circuit structure that you can actually do that as well. So there are a lot of restrictions there. This is like this is like, you can consider like we are at the crux of when the when the classical computers were born, and that is the level and the area where we are currently at. The similar situation we are in where the quantum computers are born. Probably down the line in 5-10 years you will see in already many solutions are getting solved using quantum computers, and we will see that it will start solving a lot of complex problems in next 5 to 10 years. If that being the case, then already people are started using quantum computers along with classical computers for their research activities and algorithm creation and so on and so forth. Now what we are doing is, on our classical computers we are utilizing our quantum computer for execution asset, so it's a parallel thing that we are using. So think of this expanded to your own programming structures and everything. There could be a time in 5-10 years down the line where you will have your normal programs will get executed at a much faster pace using a quantum computer, and get the result and utilize it part of your classical computer, something like that. So at the near term that we see, both classical and quantum computers work together to solve a lot of problems, and probably complete migration to the quantum computers may happen probably at a later point in time. Any research outcome which says you can build the quantum computer at a normal temperature level and so on and so forth, you can go to that level. And the second thing is error correction asset. So this is because there's a lot of errors that is happening still, that error correction is a very research specific area. There a lot of work is going on there. But parallelly, here whatever that we are talking about from utilizing the quantum computer part of your machine learning that we are doing is all predominantly a hybrid structure. That is where we are going. Qiskit is having a different way of approaching, but here in the case of Google, the approach is very beautiful, and I see that this is the approach we will see going forward for any of the implementation uh, for the quantum computers as such. Yeah, all you
Yeah.
said is true, and it has to be addressed, and it is being addressed as we speak there.
Okay. Okay. Thank you.
Okay.
Thank you, Prasanna. Thank you.
Mr. If I may add, actually, I watched a documentary
Okay.
about quantum machines or quantum computers. There is a limitation because the objective of quantum computing is a little bit different than the normal computer. For example, one of the good things about quantum computer, if you have a limited input but like a big output or a limited output, then quantum machines will help you doing that. For example, let's say you want to create a simulation of a water, then
Right.
how waters move, and you will have a limited input, but the output would be very great. For normal computer, it will require too much resource in order to create that simulation, but for quantum machine, it will create it smoothly.
Very
So
beautiful.
there is a documentary. I will share with you a link
Yeah,
later in the group. I think it will help you also understand the objective of quantum machines.
absolutely, Yusuf. Yeah, you well said. Yes, it's currently at this point in time with the limited resources, it's been mainly used on the research specific activities. But very soon you can see that it is being used mainstream. And the thing that they're talking about in terms of breaking your, your cryptos, or breaking your, algorithms for your encryption and all, we are long way ahead. Yes, it is possible. It is quantum computers are capable of doing it, but not right now. With the restrictions on the number of qubits and the number of qubit-based devices, we are long way to go to achieve that level there. Sure. Any other questions? Sure. So the next is, so till now what we have looked at is in terms of the basics of how we can utilize a quantum computing basics to create our circuit, create our gates, create our operations, and put it to quantum computer for execution. Now the actual quantum machine learning comes in, which is an intermediary or intersection of your quantum computing and the actual machine learning algorithms as such. Okay, so that is where the quantum machine learning comes in, and we will look at that from now onwards. To enable the quantum machine learning, Google introduced in 2020 a library called TensorFlow Quantum. So this was in collaboration with University of Waterloo and Volkswagen. And the beauty of TensorFlow Quantum is, under the hood, it is basically the Cirq that we just saw integrated with the TensorFlow as such. So TensorFlow as such is used for your machine learning operations for quite some time now. And how beautifully they have integrated the Cirq as part of their execution is the beauty of the TensorFlow Quantum as such. So, so before we understand, so there are some constraints in terms of how we are actually interacting in the quantum world as such. So the quantum data is very important, because we're going to talk about the data in a matrix structure or a vector structure, because we'll be interacting with the qubits in the quantum world. But in the classical world, we may not be talking about the matrix or anything, but we'll be talking in a plain simple data, tabular data, image data, and so on and so forth. So there should be an amalgamation of this quantum data management as such as part of your machine learning. That is one important thing. And to enable this, the TensorFlow Quantum has something called hy- hybrid quantum classical models. What that means is, you have a classical machine learning models. It could be that your neural network, your typical regression algorithms, your typical tree based algorithm. These are classical machine learning algorithms. And at one other side, you have the quantum executions there. So now they have built something called a hybrid of these two, which is a quantum classical models. One example is quantum neural network is another, is an example where the neural network which is available in the typical neural network, and utilizing the quantum on top of it and create a hybrid structure, is the quantum neural network. Don't worry about if you don't understand any of this, and we will see them shortly how it is going to look like. Okay, so these two important things we need to take care when we are talking about the TensorFlow Quantum as such. So what you are looking at here is the software stack of the quantum TensorFlow Quantum integrated with the TensorFlow itself. The TensorFlow stack is, it's a classical data that it works with. So it is a classical TensorFlow stack where integers, floats, strings, and images, and so on and so forth, that you will work with. But in the case of quantum data, you will be working with the circuits and operations. And the next layer is, for both your quantum data manipulation and the classical data, you use the TensorFlow Keras models. That's the beauty of it. And the TF layer perspective, TensorFlow layers, that is, if you want to create multiple layers on the on your neural network, in the case of TensorFlow, it's a TF layers. In the case of TensorFlow Quantum, it is a TFQ layers. And from the operation points of view, it is TensorFlow operations and TensorFlow Quantum operations. And they have a dedicated execution engine for the quantum based one as part of your TensorFlow execution engine itself, which is called TFQSIM. TFQQSIM. This is integrated as part of your execution engine. So your typical TensorFlow code will automatically work with the TensorFlow quantum code as well. And all this is enabled with the Cirq as the programming framework. And at the hardware level, that TensorFlow can very beautifully work on TPU, GPU, and CPU. TPU is tensor processing unit. In the case of quantum computer, which is a quantum processing unit, they have defined it, quantum processing unit. And this we talked about this, Microsoft's, Google's Sycamore. Like this, you have many other. We will see them shortly. So this is a software stack in terms of how a TensorFlow quantum is defined as such. And Cirq as the programming framework for all the different frameworks that they have done. In the case of TensorFlow Quantum, Cirq is the same programming language. Like this, they have domain-specific operations. The domain-specific frameworks also available. For example, Open Fermion, which is the healthcare's domain-specific framework for some of the operations. Even for that, the Cirq is the same programming language or programming framework. Like this, there are like 10, 15 open source frameworks that they have put together. So these are supported cloud services. We were talking about Microsoft Azure Quantum is also supported by your Cirq programming, and your circuit you created. You can directly execute it on Microsoft, and there are various other companies. They are providing their cloud services, and using them, you can actually execute the same circuit that you have created and execute there as well. So the difference is basically the number of qubits that they allow you to utilize and experiment with that. In the case of Google, it is maximum of 30 qubits that you can use and execute. It could vary in the case of IBM's and Microsoft and so on and so forth. So that's an example there. The interesting thing is all are being provided as a cloud service. So you at your home sitting here, you can access anything and everything that you are seeing there. Okay. So when the TensorFlow quantum was created, they had some design principle as part of their goal. So differentiability, circuit batching, execution backend agnostic, minimalism is the different design principles that they've looked at as part of their when they are designing the TensorFlow quantum as such. So you can go through them at a later point in time. So they don't want to have any much bigger change in terms of the actual um, a, existing classical machine learning flow. So what they've done is, here they are considering circuits that you are creating as tensors in the TensorFlow. So using Cirq constructs to generate these tensors, we will see them in the example as such. Okay, because you are converting these circuits as a classical data, you can actually utilize them as part of your TensorFlow operations as such. So that is the beauty that they did. Circuits they are considering as tensors, and they're going to allow you to utilize that circuit as part of your TensorFlow operations as such. So that is the beauty of TensorFlow Quantum as such. So it is a hybrid model where you can utilize the existing machine learning operations as part of your Cirq, your quantum machine learning as well. Okay. So now we will see a quick practical in terms of how we create a parameterized circuits. So that is the next practical before we get into some of the machine learning part of it. So in the third practicals, I'm just going to parameterized circuits. Switch to the code, and now you can see that there is there is a code called Quantum Machine Learning Basics 3. This is to help you create parameterized circuit. Now here also I'm not installing TensorFlow Quantum, but I'm installing just the Cirq and the SymPy. SymPy is another framework used for connecting and creating some mathematical operations at a very simple way, part of your program as such. So, or you can consider as symbols. If you want to have a parameterized circuit, and you can create the symbols using the SymPy. The symbols are nothing but your actual parameters that you are creating. That parameters are called symbols. Now these parameters that you can use by using SymPy, and you can use these symbols as part of your actual circuit as such. We will see them in the practical. It's a parameterized circuit. What is parameterized circuit is a question came that uh, I have created a circuit and I wanted to have different values to be passed for different run to see how my circuit actually operates, right? Different values to be passed to my circuit to see how the circuit actually operates and how the circuit actually gives me a response. That is what is done using the parameterized circuit as such. Now I have installed the Cirq and SimFi. So I'm just importing them. So now let me take a simple circuit like this to do this as a parameterized circuit. Now I have something called Ry. This represents I want to rotate my qubit on a y-axis based on a theta value. A theta value. This theta value is the parameter that I wanted to pass it on. I'll repeat. I wanted to rotate my y-axis of the qubit by a theta value. So this theta value at the time of creation of the circuit, we don't know. We will pass this information at a later point in time. Based on that information that I pass, then this theta value should be taken, and based on which the actual y-axis should be rotated. So this is what my requirement is. And once that is done, I use a Z gate to actually read the data from there. Okay, let me just define this. Let me create a qubit and let's call it as a q0. Now we said the parameter value here, the theta is the parameter value. I am defining this parameter value as a symbol. Symbol is nothing but parameters that you are defining. Now theta that I defined. Now once the theta is defined, now what I'm going to do is create a operation rotate on y-axis for this theta. We don't know what is the value on this particular q0 on this qubit, and create that as a circuit. That is my circuit. So let me execute this. Once I'm done, I'm having a parameter value. Let's say I'm passing on 1.5 as the parameter value, the theta value 1.5 I'm passing on. So in the simulator, so previously what we will do, we will directly give the actual circuit, but now here we need to pass on this parameter value. I am saying that simulator.simulate the circuit that I wanted to simulate and the parameter resolver that I am passing on here, and get the final state vector. We told previously that everything that we are talking about, the qubits are all represented in a state vector. So this state vector details have come here to the state vector. Now the once we have done only this particular rotate operation, now the z gate I need to apply here. Z gate I need to apply. So I'm creating a z on this q0 and get the value of z0. So there is a function called expectation from state vector. Expectation from state vector, and in this I can just pass on this state vector and the qubit map, that is q0, and get the real value out of it and print it. So now if I just execute this one, I am passing it on 1.5, and when I execute this z value that I got like 0.07 something. Now if I want to change this one to say 1.2 and I re-execute this whole circuit again, now what I did is I have moved the theta value, that rotation value, I have defined it as parameter. Previously I moved say theta value of 1.5. Now I am moving a value of 1.2. Because I moved 1.2, I get a completely different result in terms of the output as such. I hope it gives you how you create a parameterized circuit as part of your program as such. Here we are creating a symbol. Symbol is nothing but the parameter, and use that symbol for your simulator when the simulation actually happens. And you can use a method called expectation from state vector to actually get what could be the value of the particular one. Using that, you can actually change the value of theta and get how much of rotation that you want as part of this circuit as such. Hope it makes sense.
Just to verify, Mr. Prasanna here.
Yeah, yeah.
So now this 1.2 represent the amount of rotation that we want, or it's a value passed to the circuit itself?
It is the amount of rotation, the theta amount that we are passing on as a parameter.
Okay. So the circuit means it's like a normal circuit, but here we'll control how much rotation this circuit does.
It is not a circuit, actually. It is that y-axis of that qubit, how much of a change that we want on that qubit.
Yeah, I get the point. Yes. Okay.
Yes, yes. Yeah.
So this basically, uh, I mean, Ry is a function of the circuit which we are applying the theta. So it can be rotation, it can be even a square root, correct?
Exactly. So you have a different function, and you wanted to do a square root or anything, that you can do that as well. Yes, correct. But in the case of square root, you may not need to pass on any details as such. You want to do a square root, probably what value that you wanted to square root, I'm not sure.
No, so that would be the input. That's what I'm trying to say.
Yes, yes, yeah, correct, yeah. This is how you pass on some parameters to the circuit as such.
But sir, here you mentioned that this rotation will be on y-axis, right?
Correct, because we used ry. This is a default gate which is already defined, and
Okay,
which
okay.
takes the parameter as theta. And that theta value, if you look at the diagram, ry rotate on the y-axis for the angle of theta.
Okay. So this can be changed to x or z too, right?
Absolutely, yes.
Okay, great.
Yeah, sure. Any other question?
Yeah, Prasanna, I have a small question. When this was introduced by IBM, the IBM quantum computing, I think around 2016 or 17 for public, there was a beta version. They had a graphical user interface where you can actually drag and drop the
Yes,
gates
yes.
and then define
You're
the
exactly.
parameters of those gates.
Yes, IBM
Do we?
provides that. Yes, yes. This
Yeah,
circuit creation, IBM provides a graphical user interface where you
right,
don't need to actually write the code, where you can actually drag and drop the interfaces and create the details. But that is from
right.
IBM circuit, and this
Yeah,
is the one IBM generates the code is in Qiskit, and this is
yes.
basically Google. They are yet to actually provide that user interface yet.
Okay.
Okay.
Thanks, Prasanna.
Sure, sure. Yeah, you're right. It is available for IBM
Yeah,
actually. Qiskit asset. It is available.
yeah.
Yes.
In those beginning days, like in 2016 or so, it was so easy, but I
Yeah.
never had a program which needs a quantum computing. So I was like using this gene, that computer grid was there, right? World grid computing. So I tried to put that program there, and
Okay.
yeah, that was easy at those times. Not sure how
Okay.
it is going on right now. Thank you.
Sure. Sure. Any other questions? Sure. So, if not, let me just go back to our presentation. So let us start looking at taking a step back on a typical machine learning algorithm, how it works, and how we can actually relate ourselves in terms of utilizing our quantum machine learning algorithm, how we are going to use that as well. Okay. So if you look at typical neural network as an example, so the first step that you do is whatever data that you got, you will work on preparing the data. That is the major part of your actual operation. Once you prepare the data, you create an input vector, and you basically give that input details, and you create how many layers that is required for the actual neural network. So here in this case, I, J, K represents all the layers that you have on the neural network, and you get at the end an output vector. And now what typically does is to actually improve the quality of the output. The target vector that you're expecting, this is as part of your training operation. What you do is, as part of your target vector, you will check for errors and evaluate the classical model that we have. And in case if we find more errors, to correct it, you will actually do something called a back propagation, where your weights and biases will get updated in the back propagation, and you will repeat the whole process here. So this is a typical neural network operation that happens. So you prepare the data, and you input the vector, and you create the layers, and you go through a step of processing it and get the output vector, evaluate error for what you are expecting the target value, and in case of more error, you go back and modify the weights and bias and re-execute the whole thing. This process you will repeat until either your error is very less, or you exhaust to a level that you cannot probably execute this more than this. You may not be able to get much better result than this. At one point in time, you stop it and say, okay, this is fair enough for my neural network, and you will start utilizing it. Here the data all are being represented as a input vector. The beauty of qubit is the qubits were also represented in vectors. So there is already a beautiful correlation between a typical neural network and a quantum computer as well. But the execution of the quantum algorithms happen in an external place, like it happens at the simulator or the device. So we may have to plug that particular gap as well. So how we are doing is, in the case of TensorFlow Quantum, how the flow is modified is, you first create a quantum data set. Okay. And once you complete your data set, you send this data set to the quantum computer that is represented in the blue to evaluate your quantum model. And once the evaluation is done, you get the output from the quantum. Now once the output is received, you are back to your classical computer. So this is a classical computer, and this is a classical computer. The blue color part is the actual quantum computers as such. So you receive the response from quantum computer, and you do the evaluation at the classical computer level, and you do the cost function, you evaluate the cost function, you see how much of error rate, and you wanted to re-evaluate the details. Now you update the values of the response, and again you update the parameters and put it back to our quantum computer with the modified value, and you repeat this whole process altogether. So one of our friend was asking about, we may require multiple iteration. This is exactly the multiple iteration here. For each and every iteration that we are doing, we may have to go back to the quantum computer for executing our network, and executing our circuit, and get the result, have that result mapped to our classical machine learning model, and use that one for our evaluation as such. Okay, I'm talking at a very high level. Let's see step by step as well in the next couple of minutes. Okay, so this is the high level flow of how we are integrating our classical models with the quantum machine learning as such, quantum models as such. So now, to give you a perspective, we're going to see a list of steps that we're going to follow as part of providing this detail. Now, these steps that we will follow in the practical now to actually have the complete end-to-end of the machine learning operation happens. So the first step is our import of the data, whatever the data that we wanted to do use, and we will import the data, and your EDA that you will perform on the data. You pre-process the data and get the final processed data, and you may have to encode the data in a way that that data is utilized, can be utilized as part of your quantum machine. And then you build the quantum neural network and use this data to train on the quantum neural network, and you basically visualize the result. So this is the different steps that you follow in terms of uh, executing your quantum machine learning algorithm as such. So this I am touching only the basics of it, and there is a lot more are available. And the TensorFlow quantum as such framework provides lot many algorithms which can actually work along with your classical machine learning algorithm combined with the quantum machine learning algorithm. So you can always go back and refer to those one. So as part of this, I'm taking one simple example for demonstration. This demonstration is provided by Google TensorFlow, the same thing that I'm taking for your representation. Okay, there is a image classification on MNIST data using TensorFlow Quantum and Cirq is the actual problem that we are going to solve now in a practical way. Okay, so before we get in there, let me just give you some of the libraries and the details that we are going to use as part of the code. So these are utilized as part of our code now. So we just talked about SymPhi. SymPhi is for symbolic parameters to the circuit. You can use SymPhi for passing some parameters as part of your as part of your program. That is one. There is we know the fact that print circuit. Once you created your circuit, if you want to print the circuit, you can just go and say print circuit. It will automatically print your circuit, right? But there is another library called SVG circuit. This SVG circuit is going to help you print in a very very beautiful way. Okay, very very beautiful way. So that is called SVG circuit. The next is a quantum neural network that we're going to look at, and there is another operation called .xx. So which is a tensor product of two x gate are represented by Cirq.xx. The tensor product of two y gate is represented by .yy. Okay, so what is this tensor? Actually the tensor as such is uh, representation of the data on your TensorFlow has to be in a tensor format. TensorFlow, the basic premise is how you are going to represent the data, because the data will be, it is like a vector format. That is what is called tensor. You represent your data in a vector format. To simple understanding is a tensor representation. Now, if you do two tensors and do a product of two vectors and do a product of these two vectors, that's called 2x gate. If you do that with x, then it is a 2 tensor product of 2x gate. It's basically a vector product of 2x gate. Okay, to simplify, to y meaning 2 vector product of 2y gate. So that is what is there. And so we will look at the practical in terms of how we're going to do this one directly. Okay, let me just go here. Now there is a fourth uh, you know the document that is shared. This document is already available in the TensorFlow, and also there is a modified version from one of the other person, which is a much simpler explanation of this. The one available in the Google is much complex, but this is a simpler explanation. I've taken that, I'm sharing it, so all the credit goes to them, not me. Okay, So let's first look at what we are planning to do. So we are going to do image classification and on Fashion MNIST dataset from TensorFlow Quantum and Cirq. Let's first understand what is image classification. This MNIST dataset, the dataset consists of 10 different classes of images. Class meaning image classes. For example, it could be shoes, it could be dresses, it could be like lot of other details, like your sacks, your pant, and all those things. These are fashion MNIST dataset. So all these different images are available as part of this MNIST dataset. So that there are 10 different classes are available. Classes meaning pant is one class, shirt is one class, and your shoes are one class. So these are different classes. So 10 different classes are available as part of this data set. Okay, and we're going to use this data set, and we're going to do an image classification of this data set. What is image classification? In the sense, say if once your neural network is ready, when I give an image, it is going to tell me on which class this particular image belongs to. To give you an example, after my machine learning model is ready, if I share an image of a shirt to that particular machine learning algorithm, it should tell me that it is a shirt. So that is what image classification. So that is the actual one that is being done. Okay, so this is what we are planning to achieve. But instead of this can be achieved using your typical machine learning model itself. The reason why we are here is to actually utilize TensorFlow or TensorFlow Quantum so that we can see how we can utilize the quantum computing for our implementation as such. So that is our goal. So we're going to start from beginning and see how things are going to go as such. Okay, because it is a large installation required, I will just walk you through the code. You have the code already with you, so you can, the TensorFlow Quantum installation takes anywhere in terms of 5 minutes to actually install it. So it is a waste of time, so I don't want to reinstall it. So you can actually execute and enjoy your things there. Okay, so now first thing is you install your TensorFlow as such. So I'm installing 2.3.1, and next is TensorFlow Quantum. I installed 0.4.0. There are current version is at 0.6.0 something, and there are some problem in the current version. So I'm just reverting back to the older version of the code. Okay, and we installed Cirq for our actual circuit as such. So the next thing is we are importing all the libraries that is required. TensorFlow as TF, NumPy is for our matrix manipulation, NP, and model selection. Basically, import train test split. If you have a machine learning model creation, the first step you will do is when you take the data, you will split the data into multiple category. One is train, test, validation set, and so on and so forth. To do that, there is a framework sklearn. Scikit-learn actually provides a library called train test, train, train test split. You can utilize them directly. And specific to quantum machine learning, I'm using TensorFlow Quantum as TFQ, Cirq, and SimFi. And now we talked about SVG circuit. This is just to give you a beautiful circuit diagram. That's it. That is what we'll get out of this SVG circuit. And the matplotlib library is to plot your output in a very beautiful charts and graphs. That's the purpose of it. I import all the data, and I will see the simple version of it. And I am importing the data set. The data set is by default comes part of your TensorFlow. I am importing the Fashion MNIST data set as a data set. Once I import it, I load the data in training and test data set. So typically any data will have two items. One is training data and test data, and also you will have x and y. X and y represent, x is the list of all the features that you are using, y is the target variable that you wanted to achieve, meaning x is all the parameters you use for classifying whether the particular image is a dress or not, and y is the one will say whether it is a shirt or pant or something like that. Okay, so 10 different classes are there. Let's look at the shape of it. And the shape is basically it has around 60,000 rows and 28 features for your actual um, actual shape. In the case of this is for the training, in the test you have 10,000 rows and 28 features. Okay, now because we are going to do using qubits, we don't want to take uh, multiple classes. So we told that we have around 10 different classes of data. That is, you have your class in terms of your shirt, pant, and so on and so forth. We don't want 10 different classes. With rather, we wanted to have the class only specific to two class for our implementation. Okay, so here there is a helper function. This helper function will basically filter based on y value 5 and 9. You can change this to any two class that you want. Okay, and I wanted to keep only this as part of my execution. I don't want any other class. So I'm going to work only on two class classification. You can consider as two class classification. You have shirt and plant. You build the machine learning model. Once you build it, when you give a shirt, it will tell whether it is shirt or not. So, or if you give pant, it will tell whether it is pant or not. That's a two class classification that we are going to build. So this I have created this as a sample helper function, and then call this function with our training data and test data and get the result. And when I see that result, I get the detail as now out. Initially I had 60,000 records. Now only with two class I have only 12,000 record, and in the training it is 2,000, in the test it is 12,000, it is test it is 2,000. That is enough for me. Let us look at the image of this particular class. This has an image that we are visualizing, and this has, if you look at has 0 to 250. So we need to normalize the actual image to probably 0 to 1. So if I divide this by 255, then I will get the normalized class where the data will be within 0 to 1. So if you look at the same image, nothing has changed, only that your range has become reduced from 0 to 1. This is a typical normalization that you do on a machine learning. And once you get it, and next thing is you need to flatten your actual image now and resize the actual image. We don't want uh, you will have RGB because it is a color image. You have RGB value 28 to 28.1. We don't want all the details because we work with qubits, and the qubits are going to have only probably two values as part of them. So we need to actually reduce the number of uh, RGB values that are part of it. So I'm going to downscale the image to a 2 by 2, and you resize that particular image using this code. So once we resize it, we get the image like this. Okay, so which is within the normalized one, 0 to 1, and all these images are available for us to. This is kind of the image that we're going to use for our classification as such. Okay, and the next is from using the train test split, I'm going to create a validation data set as well. So now previously I had test data set, I will create a validation data set. So this 1,200 12,000 records, I'm going to split it out 10,200 for my training, 1,800 for my validation, I already have some 2000 for my testing assets. Okay, so until then, now we have our data processed. Now this data has to be encoded. So the encoding as such, if I just take the extrain data, if I look at the extrain data, the data is going to have, let's say, 4 values as part of it, and the values are in terms of 0 0.1, 0 0.4, and so on and so forth. Because we are going to use qubits, what we're going to do is, to simplify the whole operation, we're going to classify these into two different values. In terms, if the value is less than zero point 0.5, I'm going to keep that value as 0. If the value is greater than zero point 0.5, then I'm going to keep that value as 1. So here, if you look at the x train of 0, currently has 0 first value, second value is zero point 0.4, which is less than zero point 0.5, so I can consider this as 0, and zero point 0.7, which is greater than zero point 0.5, I can consider as 1. So does here. So this is a binary encoding that I'm doing. So it's a small helper function which is actually doing the same thing what I told, which looks for a threshold if it is less than 0 or greater than 0, based on which it will actually create that. You pass on the extrain to the binary encoder and get the result. Now the same code, if I execute, now you can see that the output is 0011. It has encoded into 0011. Now we have done this operations for training. Now the same thing has to be done for others as well. So before that, uh, now we need to create circuit for our image as such. So here, this encoded image is being passed on as the parameter, and this encoded image will be converted into a circuit. Because it is an image, I'm creating a qubit with a rectangle of 2 by 2, 2 by 2 rectangle that I'm creating, and that is going to have 4 values. Like here we have 4 values, the same 4 values will be inserted into that particular qubit that we are creating. And here, this circuit that I'm creating, and I'm appending each and every image that I'm creating here as part of this particular circuit. Okay, so now once this is the create circuit from image, this that I'm encoding with the training data. So the from the training data, take the encoded image and pass it on to this create circuit, and that will create a circuit, and the output will be a circuit that will be returned as part of my final output. So that will be there as the final output. Now previously, when I looked at x train of 0, I received a simple set value of 0011. Now this value I've converted into a circuit. Now here is the quantum machine learning part comes in. So circuit. So now when I look at it, it is basically a 2 by 2 value. 2 by 2 value will 2 by 2 rectangle will have 0001 1011. 4 values will be there. Now if I look at this zeroth value, here the first two qubits does not have anything, only this 1011 has the value. So that's where we are seeing that these two has a value, that value got x gate being applied there. Okay, so that is what is represented here in this particular print statement that we are seeing. So now TensorFlow Quantum provides a beautiful option of converting your circuit to a tensor. Converting your circuit to a tensor. Now here what we can do is, TFQ is the TensorFlow Quantum dot convert to tensor will convert this to a tensor, and the text train, the circuit that we have got, is converted to a tensor now. So now we're going to call it as X train TFQ. Now the same way we are applying this for validation and the test data set. Okay, so whatever that we have applied the same, and we are getting this is a training TFQ, and we have X validation TFQ and testing TFQ. All are in TensorFlow Quantum that we got now. Now the next step is, so till now what we have done is basically prepare the data, process the data, and the next step is we need to build the quantum neural network as such. And once we build the quantum neural network, we need to train it on the quantum neural network. Okay, so the quantum neural network, I'm going to define it as a simple class, and so this simple class will be initialized with data qubit and readouts. These two are the items that will get passed on as parameters. Using that, you have multiple option in the QNN. Either you use add a single qubit gate or a two qubit gate that you can add, and this qubits gets added as on when it gets passed on to it. Okay, so it gets appended to the circuit as part of it. Okay, and if you want to add a layer, because it's a neural network, you can add a layer as part of the similar way. You pass on the circuit gate and what is the symbol that you wanted to uh, pass on. Using that, you can add a layer as part of your QNN. So these are methods that will define the QNN, quantum neural network. Okay, this is to represent in terms of how the quantum bits are being manipulated there. Okay, so now once we create this quantum neural network class, we need to create the QNN, that is like creating an object for it with passing on some of the values that we got. Okay, so you create a, a grid qubit, and you create a grid qubit. This one is basically for representation readout purpose. You are creating it. When you see the diagram, you will understand. And you create a circuit with this particular item and append this X for the readout, H for the readout, and you create the data qubit and pass it on to the data qubit, and readout that you created, you pass it on to this QNN. The QNN takes two parameter, data qubit and the readouts. The details are being passed on to them as such, and you create layers. Now here, as part of creating the layers, you use this tensor product of cirq.xx and cirq.zz. Okay, so this they are doing. I really don't know why they are doing it. Probably I need to dig more to understand how the actual operation is being done there. Okay, and they are appending this readout, and they are returning this particular item there. So they are calling this create QNN, and once they call that particular model, and the model readout will get created. When you display this detail, that is what is displayed here. The circuit detail gets displayed here in the, this is a quantum neural network circuit that you got created. Okay, now here, this is for your display perspective. The readout is only for readout perspective. The first row you can ignore. So the second rows, second, third, fourth, and fifth, where the actual data item that you are actually processing. Here, if you look at here, what we are doing is a XX gate and ZZ gate that is being applied. This is a tensor product of Z gate, tensor product of X gate is what is being applied on each and every qubit that you have passed on. So here what is being passed on, you have in the X, we have four items in the, we have looked at here, there are four items in the X, and these four items are getting converted into four different items. Here you are displaying two because the two items are zero, that is not getting displayed, and effectively wherever it is one, this particular data gets displayed there. Okay, so now the four items, the four values, the four grid values will get applied with this XX gate first, and XX on this, and this, and then the ZZ gate is being applied. One, two, three, four, and then the last one is the Hadamard gate, and the last one is the readout that you are doing at the end as such. Okay, so this is what is being applied here. So once that SPG circuit, this is just to display. It is like a print of your model. You created the QNN, and you created the Q model, and model readout details have come out as part of the outcome. And how the structure looks, this is how the structure actually looks. Okay, now is the interesting part. We're going to combine both the typical TensorFlow layers along with your TensorFlow quantum layers as part of your sequential Keras model. The sense, when you create a neural network, you basically have multiple layers. We looked at here, you will have multiple layers, right? These are considered as layers of neurons. So now here we're going to have both TensorFlow layers. This could be a TensorFlow layer and a quantum layer. That is what we're going to do now. So here, coming back here, we're going to create a model with TF Keras sequential. It will have a Keras layer, and TFQ layer is nothing but your TensorFlow quantum layer. And this TensorFlow quantum layer will have something called parameterized quantum circuit. PQC is nothing but parameterized quantum circuit. These two will be put as part of the layer as such. So here the input for this PQC is the model and the model readout that you got, that will becomes the actual input for this particular Keras model. Okay, so that you input and you basically execute, get the actual value. And there is to validate the loss. So typically you will use, in a typical machine learning operations, you will use a different loss function. There is a special type of loss function called hinge loss. Using that hinge loss function, you basically validate the actual machine learning model that you are trying to create. Because this hinge loss that you are using, because you are using the quantum machine learning part of your execution as such. So what is this loss we are talking about? I'll just go back to the presentation. See, currently assuming that you prepared the data, you put the input data to the machine learning, it comes out with a response output. But what you are expecting is something different. Your target vector that you are expecting is completely different. So the actual difference between your target vector and the output vector is the loss error that you are thinking. And to correct this error, or to reduce this loss, you basically go back and re-evaluate the weights and bias. That is how the whole flow actually happens in a typical neural network. So to evaluate this loss, uh, so there are various loss functions are available. So you have for a simple algorithms, you use like RMS loss function and so on and so forth. But in the case of neural network, here they are using, because it's a quantum neural network, they are using this hinge loss function. Using that loss function, they're going to evaluate this particular operation as such. So you evaluate the operation, and once that operation is done, you get the value of, you re-evaluate and re-execute the details, and actual hinge accuracy you are defining it here. And once it is done, you basically go for compiling your model with the hinge accuracy, with the actual loss details that you are providing. And you do a fit on the model to actually get how well your model is actually trained. Okay, so the validation data you are passing on here, we are doing a 10 rotation, then 10 iteration of execution as such, as part of this. At the end of the 10 iteration, when you do a model evaluation, we get a loss of around 0.3, 35% loss, sorry, 3.5% loss, uh, sorry, 35% loss. And hinge accuracy as such is almost 82% accuracy. That is, this represents that if you, assuming that we have taken shirt and pant as a two class classification, and we wanted to identify, when you put an image, there is a 82% possibility that this particular algorithm will come back and say whether it is a shirt or pant. So that is the accuracy level that you got. So you can visualize how the execution actually happened using this plot operation. Using that, you can see from a model accuracy point of view on each and every epoch how the accuracy has increased. Similarly, how the loss has reduced. This information can be represented here. So this is how you basically combine your typical TensorFlow machine learning execution with the TensorFlow quantum execution with the circuit. So the way in which they have done is they have simplified the whole execution operation. You will execute as if you are executing a simple machine learning operation, but internally the TensorFlow quantum takes care of executing it in the TensorFlow and sorry, on the quantum devices or the simulator, and bring the result. Here, here in the case of TFQ configuration on the Keras, we have not mentioned anything about whether it is a simulator or the device and so on and so forth. Here, there are various hyperparameters that you can provide in terms of what quantum machine that you wanted to do the evaluation with or the execution with. You don't need to do anything. The TensorFlow quantum will automatically take care of executing this in the quantum machines and bring the result and have it converted part of your TensorFlow matrix and provide that result there. So that's the beauty of combining both the typical TensorFlow operation and the TensorFlow quantum operations as such, right? There is a lot to actually absorb here, and probably you may this code I have shared it across to you guys, and you can probably go through them and understand more about it. And when it comes to the gates, why they are using this XSZZ gate, I still need to understand more about it as well. Probably once I get hold of the details, I can share it across to you guys as well on that. So that brings us towards the end of our session in terms of quantum machine learning assets, how you can use as part of your day-to-day machine learning operations as such. So any questions, team?
So in this model, okay,
Yeah.
we were basically reducing our data set, okay, to
Yeah.
map them, I mean, quantum, this one, correct? So how does
Correct.
this practically apply
Yeah, you are
when
right.
you're having
Yeah. Yeah, so many of the actual data that is being lost here, because it is an image data, probably we may have to reduce that to a very smaller qubit level, so that we are losing a lot of data as part of the process as such. Okay, so you are absolutely right, and we should not do that. But because we have restriction in terms of number of qubits that we can use as part of your quantum machine learning, we are reducing this. We can go up to 30 qubit, probably to that level. The number of qubits, number of values that you are using for the qubits, that you can increase, but still there are a lot of restrictions in terms of what kind of operations that can be applied there and take it forward. And this is available for us, and some of the simpler operations that we are currently we need, probably you can start utilizing them here, utilizing these machine learning operations. But as they bring in a lot of algorithms, and as they bring in a lot of new circuits or new quantum machines with more qubits and all, probably we'll have enough breathing power to actually use large amount of data for our processing as such.
okay, the other part is Okay, I mean, um, see, if we use the TensorFlow and other thing, the other part about the machine learning is, okay, how many variables or how many parameters I need to consider for my machine learning. Okay,
Right.
so that I need to represent as a part of my input data. See, the way I look at it, I do pre-processing outside the quantum this one, and then I need to create. I need to move the data set to fit my qubits, and then though Keras gives me uh, can allows me to process both. Okay, fine.
Right.
And then I need to finally process and then get the result back. This one. So that's
Correct.
the idea. Okay.
Correct.
The
Right.
main part is can a partial can be done, or it has to be fully that particular circuit has to be fully applied within the this one. That's what I'm trying to understand.
So partial meaning as such, so effectively, if you look at this is from a classification perspective, this circuit is being provided.
Yeah.
Like
Yeah.
this, they have given circuits for various different problems. By default, they have built the circuits for us already. It is just a matter of we utilizing these circuits for our specific operations as such. We don't need to worry about that as such. Probably, yes, partial circuits, your own operations that you wanted to do on manipulating this data. That is a part you can further dig more about it and get more understanding on this. Yes.
Okay. And do we have any specific, for example, take the same scenario, do we have any specific benchmarking? And as you said in the first part, the cost, correct? So do we
Right.
have that knowledge, assuming that you don't use this and we do it only on our traditional way? How much is the
Yeah.
cost difference or this one? Do we have that detail?
Yes, the in the Google as such, they have as part of their experiment, they have benchmarked it. They have provided part of the TensorFlow quantum website as well. Okay. And for the same case study also, they have taken a benchmarking. Like, if they are doing the same exercise with the classical machine learning, and what kind of an improvement that it is giving, and if I do with quantum machine learning, how what kind of an improvement it is giving. So those comparison also they have provided there. Yes.
Thank you.
Hope it makes. Yeah. Yeah. Sure. Wonderful. Any other questions? So thank you very much. I think thanks for patiently being here till end. So to understand how do you actually start work on the quantum computers, create our circuit and deploy it on the device, and also see how we can actually have quantum machine learning being integrated part of our solution as such, and deliver that quantum machine learning as such. So thank you very much for your time and patience. And I will be sending the recording of the session once that is done. I don't know, for some reason the recording has stopped in between. I'm not sure till what time it was recorded. So I will share that details, whatever level it is there. I will share it across to you guys. Okay. Thank you very much. I hope to do. It is a collaborative exercise. If you guys wish to do any sessions, I'm happy to listen. Probably we can arrange a session like this, and we can have the session with all as well. Any topic that you are interested and have experience and expertise on, that we can plan it as well. Okay. Thank you very much for your patience and the time.
Thank you, Prasanna. Thank you so much.
Many thanks,
Uh,
Prasanna. It's
Thank you,
really
Prasanna.
clear and
Yeah, thank
detailed,
you.
very, very clear. Thank you.
Yeah. Thank you.
thanks a lot.
Yeah, great,
Thank
great.
you, Prasanna.
Really appreciate.
Yes. ஏய் இதுல கூட நம்ம பேசலாம் போல இருக்கே இனிமேட்டு Lax, Shan, Mr. Lax.